Yeah, so welcome to the third day of the faculty development program on VLSI Design using eSim and Open PDKs. Yesterday and day before, we see wonderful talks by the FOSSI managers, Professor Kanan and Professor Prabhu. Then Steve demonstrated us the Maker Chip EDA platform. Professor Sangeeta from Dronacharya talked about the EDA tools and Professor Inderjit talked about analog simulation. Okay, so let's see what we will be talking about today, what we will be listening to today. So Professor Rakesh Sinha will be talking on modified nodal analysis, and Vipul Sharma, who is a founder of Navia Labs, will be talking on exploring Sky 130 PDK with eSIM. Okay, so yeah, so let's introduce Professor Rakesh Sinha. So from circuits, so he will be talking from circuits equations to simulation and introduction to modified nodal analysis. So Professor Rakesh did his BTech in electronics and communication from Kalyani College and Government Engineering College, and he did his uh, uh, PhD from IIT Kharagpur in 2011, as you can see, and he has lot many other things in his profile. He worked in South Korea as a postdoctoral researcher and also served at various organizations. And currently, he is a assistant professor at Electrical Engineering Department, NIT Rourkela. Okay, so over to you, Professor Rakesh Sinha.
Uh, Thank you, Shumanta, for the nice introduction. So, let's directly begin the talk. And during the talk, I'll basically try to discuss various aspects of basically circuit simulation, how basically the circuit simulation basically perform inside the simulator. So, mostly what we have seen that when we do circuit simulation, any simulator you use, we draw the schematic and then we run the some kind of simulation and you got the output. Okay, so behind the scene, what are the things happen? So that will basically try to introduce to the students and the faculty member, those who are not aware. So some of you may be aware of this MNAN thing, and some of you may not. Okay, so start and begin. Let me share my slide and just a minute. Enter screen. Better. Uh, Allow output. Yeah. Okay. Enter screen. Here. What is the problem? So sharing option, Windows, and actually this sharing option is disabled for me.
Just 1 minute, we will enable it.
Are you using different account?
Yes, yes, I am using this my personal Gmail account, so that may be the reason. Yeah.
One account already have Rakesh Sinha name. That is already co-host.
Okay, so let me check it again. No, share option is disabled for me. So r.sina30, so that account, did you have enabled that?
I'm not able to see that the R. Sinha particular name, any name.
Particular name, just a minute, let me check. So it will be in top, I hope so. Let me check. Yeah, Rakesh Sinha. Yeah, it is that this one. Meeting host is there. But when I am trying to share my screen, so this sharing option is disabled for me. Just a minute. Enter screen. Select. Now, fine. Okay, thank you. Okay, so is it visible, my screen?
No, not yet. Yeah, now it's visible.
Okay.
Now it's visible.
Yes, yes.
I'm just changing. Control L. Okay.
Yeah, slide is changing. Yeah.
Okay. Good morning, everyone. So in today's talk, I'll try to discuss from the circuit equations to simulation. Okay, so basically all of you have learned about basically solving some kind of network equation in your network theory or basic electrical or some other courses in your electrical engineering or electronics engineering, that how to solve some kind of equation by hand, so that you have, all of you have learned. But how this computer solve, okay, when it comes to the large circuit, okay, which is very difficult to solve by hand, how computer automatically solve that. So that core idea behind that is basically modified node analysis. Okay, so before going into the modified node analysis, I'll discuss about the node analysis and then tabular formulation, and then I'll go to the modified node analysis, that is the final basically current state of art of basically solving any kind of circuit equation. Okay, so yeah, so gradually I'll discuss. So why do you need circuit simulation? Okay, so the main reason is basically when you going to fabricate a chip, so there is various specific stages are there. At first you will have some kind of specification. Let's say you are designing for a particular goal. Okay, so the goal must be satisfied. So for that you need to create a design. Okay, so there are some standard design procedures are there. As per that you create the design and you draw the schematic. And once you draw the schematic, you need to do a spice simulation, and then you can go for a layout. Let's say if you are doing a chip fabrication or a PCB one, okay, so you can go for a layout and then you do a fabrication. Now, if you see some kind of defect is there in the fabrication and things, then you recheck your simulation and then fix that process, and then the process will continue. So that is a typical flow of that. Now, modern VLSI ICs, so there are billions of transistors. And so the fabrication, every time if you want to check the performance of the circuit by fabricating it, then it's a very expensive procedure. Okay? The fabrication is very costly. Okay. Now, how to solve that? So we basically mimic that. Okay. So we basically create this mathematical model, and using that mathematical model, we try to basically check whether that my circuit is working properly or not. Okay. And then if I see that, okay, there is some kind of problem is there in my circuit design, then I basically try to solve that particular portion and then again resimulate, and that procedure continue. Now, this simulation enables so basically verification, functionality, timing, power analysis, parametric. If you want to check that if you change a particular parameter, let's say resistor value or capacitor value, how it affect. And because in real time you can see that because depending upon the temperature and the other factor, your component values getting changed. Okay, for example, the resistor is not remain same resistor as your temperature increases. Okay, and maybe your performance of your transistor may degrade depending upon the as the heat increases. Okay, or the temperature increases or decreases depending upon that. So this kind of parametric evaluation is also very important. And another aspect is what if the design explosion. So what if I change something, how it affect the overall design performance. Okay, so depending upon that, we basically need some sorts of simulation. Okay, so that's basically spice simulation mostly do. And not only that, there are other kind of simulations are there, network parameter simulation. So those are mostly covered in the RF circuit. So basically it's parameter simulation and then other things. So those mostly basically covered in the basically parameter simulation. Parameter simulation problem is a little bit different from this basically you can say M&A solution or basically circuit simulation. Okay, a little bit different in some sense, because we don't exactly provide any voltage or current. Instead of that, we basically assume there is some virtual ports are there, and based on that we basically perform the analysis. Okay, the code idea basically changed since 1975. So it was basically the first introduction of modified node analysis, that was Ho and et al. So they basically introduced the concept of modified node analysis. Okay, now I'll discuss that about the modified node analysis. Now before that, I'll show you that some of my undergraduate student and one intern, they have designed one circuit simulator. Using that, we can basically perform a small sets of circuit analysis. So that is very easy to do. So let's check that. So small circuit I'll basically do. And for just a sake of I can set the value, let's say this is something 5 ohm, and this resistance, let's say 10, and this voltage, let's say 5 volt. Now I can run the DC analysis. I need to set the ground. I have forgot to set the ground, so that is the problem. So I have set the ground, because without that it does not work. So always you need to set a ground. I have specified this is the value. Okay. Let me check. DC analysis. Maybe some error is there. So basically we basically draw some circuit and then we basically do the analysis. Okay. And now that how this analysis basically carried out. So basically the core concept is basically M&A. Now how this M&A works. So the M&A basically works based on the Kirchhoff voltage law and the basically element stamp, or sometimes we say constitutive relationship. Okay, so KCL and KVL all of you are familiar with. So in a particular node, so all the basically algebraic sum of the all the currents is equals to 0. So that basically includes the current leaving, we say on always positive, and current entering is negative. So in that way we say the total is basically equals to 0. And similarly in a loop, the sum of all the voltages, algebraic sum of all the voltages is equals to 0. So that is the KVL. KCL and KVL all of you are familiar with. So KCL, KVL are basically analogous to Maxwell's equation. That I am not going to in details. Basically they are basically analogous. And then you have the element constitutive relationship. So that basically determines how the voltage and currents are related. Okay. So typically if you have a resistor, then V equals to R into I, and capacitor I equals to C into dV dt, and V equals to L di dt for an inductor. So like that. So all the elements have it. And in a phasor domain, we basically write everything in a capital case. Okay. And then we assume a harmonic current is there. So based on that, harmonic current or voltage is there. So it is j omega t. So that factor basically leads to this derivative. The j omega is coming. Okay. Now, the nodal analysis is thus basically the starting point. So in the nodal analysis, what we do, we basically consider a particular node as a ground node or zero potential. With reference to that, other nodes are basically, we basically set different potential. Okay. So for example, remaining nodes are basically assigned as V1, V2, V3, and Vn. So these are the potential of that node. And then we apply the KCL at each node, and then we express the linear system as a Y into V equals to Is. Is stands for the source. Okay, V is the nodal voltages. Okay. Now, if you solve this voltage, then we can also find out the branch voltages. So if you are able to solve the node voltage, you can easily solve the branch voltages. Okay, so that is the typical way of solving this standard node analysis problem. Now, the problem is that it works well for resistor, capacitor, independent source, and voltage control current sources. But when it comes to the voltage source, so basically specifically ideal voltage source, if you have a practical voltages, still we have some way to basically incorporate into the analysis. If you have an inductor and if you want to perform a time domain analysis, then in that case also it is a problematic. But if you want to perform some kind of frequency domain analysis, it's not a problematic thing. And frequency domain or AC analysis. Okay. And then if you have a current control source, though in that case also it does not work so well. Okay. Now for an example how this node analysis works, so in this particular node we will apply a KCL, in this node we will apply a KCL, and then we'll combine that and then make a matrix equation. So here the is the source, and that equals to V divided, so the current going, okay. So V divided by this R3, okay. So I have missed that, okay. I have this slide, I need to skip. I've changed that, but why it has not? Okay, so directly comes to the graph-based analysis, node analysis. Now, this is a typical standard procedure for the nodal analysis if you want to write a computed program on simple nodal analysis. Okay. Now, in this case, we'll consider this practical voltage source. A voltage source plus this resistance is a total source. Okay. So this is a single branch. This is another branch, and then you have this is let's say this is branch 2, this is branch 4 and 5. So branch are basically inside the bracket, and the nodes are basically inside the circle. Okay, so in that way, we basically make the notation. Okay, and we have also predefined direction of the current. So the direction we have defined like this. This is the predefined direction of the current, and in this way, we form a graph out of it. Okay, so basically, instead of writing down the capacitor and the inductor explicitly, we have created a graph out of this. Okay, so the graph having the nodes and the branches. So nodes are basically this circle, and these branches are this line. Okay, so this is a way of representing a network in terms of the graph. Now, once we write down this network in terms of the graph, we can write down the KCL and KVL in terms of the graph. We'll tell later on. Okay. Now, another important thing is that we need to talk about the branches. How we'll basically write down the branch equation. Okay, so that is a very important factor. Now, for a nodal analysis, we need branch current equation, not the branch voltage equation. Let's say we have a general branch having some kind of element is there. It's a inductor, capacitor, or resistor, whatever the element is there. So we basically represent it by YK, the admittance of that branch. And then it is having a voltage drop across this. So this voltage drop across this branch is VK, and it is having a source also, VSK, and it is having a the voltage source, and it is having a current source also, ISK. So these are the sources it is having, two sources. So we have considered that it's content all the thing, but in the practical scenario, maybe both of the sources are basically zero or switch off. Okay, or maybe one of them is there, another is not there. Okay. Now this current is equals to this source current, this current plus this current. So how much is this current? So this current is basically the current going through this one. So what is the drop across this? Drop across the VK minus VSK into YK. So that is the drop into your basically, if I write the admittance into the drop is equals to the current. Okay, so this current plus this current is equals to total current. Now, if you form a matrix equation out of this, so this is a particular for a scalar equation for a particular branch. Now, if you have a multiple branches are there, so you can make a matrix equation. Okay, so these are basically S stands for the source, and B is the basically B number of branches are there, and YB is the B cross B matrix. B is the number of branches. Okay, and BB is the basically the branch voltages. Okay, and IB is the branch current. Okay. Now, this branch matrices for what this particular example we can write. So ISB equals to 0 because here no current source is available. So all the nodes don't have any current source. Now, in the first branch, we have a voltage source, and then we are writing minus BS1. Okay, so why minus? Because of the notation. Okay, so we have considered this notation like this. So this is my voltage source, and then what we have considered the polarity is like this, and the current is basically flowing like this. Okay, now here we have the direction of the current. So here the direction of the current from this one positive to negative, but here what we have considered this direction of the current, so it's basically going out of the positive node. Okay, going out of the positive node, so basically negative to positive. So that's why you have a negative sign here. Now, if you feel the branch admittance matrix, so it's basically a typical diagonal element. So all the branch, so branch 1 having R1, so that is basically I'm writing as a G1, 1 divided by R1, and then branch 2 is the capacitor, so S into C2. So basically this is named after all the branch number. Okay, so 1, 2, 3, 4 like that. Okay, and then branch 4 having a resistor, so that we can write as a conductor, so G3 and G4 and so on. Okay. So in that way, we basically fill the branch matrices. You have branch source voltage, source voltage and source current. Okay. So this way we basically fill. Now, next thing is basically you have to construct the incidence matrix. So incidence matrix is a very key role here to construct the KCL and KVL equation. Okay. Now, the incidence matrix is a n plus 1 cross B matrix. Okay. If n is the number of basically non-zero nodes, so zero node or the ground node is plus 1. So that is what we are considering. And we basically perform n cross B matrix. So basically A matrix is most important than complete incident matrix. Okay. Now, how it is defined? If J is incident at a node I and orient away, it's going away, the current. Okay. And if J is incident at node I and orient towards, basically current is inside. So in that case, negative. If current is inside and it's negative, and then current is going out, it's basically positive. And otherwise, it's basically 0 if it is not incident. Now, the rank of this matrix is typically n. So if it is n plus 1 number of it, the rank is n. And so therefore, one row is unnecessary. So therefore, we use the reduced incident matrix A. So this is basically typically used. Okay. And for example, in this graph, if we try to fill, let's say node 1. Okay, node 1. Okay, so node 1 or node, yeah, node 0, or let's say node 1. Okay, so node 1 we are trying to fill. So in the node 1, branch 1 is in, this current is inside, so therefore negative. Branch 2 is going out, positive, and then branch 4 is going out, it's also positive, and rest are 0. Similarly, others are filled. Okay. And once you get the complete incident matrix, you can make it the reduced one, the datum node, you don't need to write, or you can directly don't write the datum node or the basically reference or ground node or other node if you write. So it looks like something like this. Okay. Now here is the very interesting fact. You don't need to explicitly write the KCL and KVL. Okay, so once you draw the circuit inside the computer, it will automatically create a graph and it will also create the incidence matrix. You don't need to write. Okay. Now, A is the incidence matrix. A into IB is equals to 0. So this is the definition of KCL in terms of the incidence matrix. Now, why it is the definition of KCL? You can see here the sum. So if we project the IB here, okay, so if I project the IB, so here I minus I1 plus I2 plus I4 is equals to 0. So this is the meaning of this. So at this node, the sum of all the current is equals to 0. So if I have a matrix into my current vector, branch current vector is equals to 0. Okay, so that is the meaning. Similarly, I can show it for node 2, node 3, and so on. Now, what is the implication of KVL here? The implication of KVL is that VB, the branch voltage, equals to A transpose into node voltage. So that is also very interesting fact. Okay. So because we have done in a specific way, so if we take a transpose and then if we do like that, so you have a this is my 0 potential. I'm not basically writing that. Okay, so N0 is a 0 potential. Now, if I want to see what is the potential at this branch, so at this branch, the potential of this branch is basically negative of V1. Okay, so that is the thing. So it is basically negative. So because this is not there, so you have a this matrix if we consider. So negative of V1 is the potential of this branch. Similarly, if I try to see the potential of the branch 2 is basically V1 minus V2. It should be. Okay, so potential of branch 2. So basically, this is the branch 2. So V1 minus V2. This is V1 minus V2. So like that. So all the branch potential, we can figure it out. So these two are fine. Okay, so now I need to again get the branch equation. Now from the branch equation, if I multiply both the side with IB, then I can get this sorts of equation. Okay, so and then finally, if we substitute all the quantities of this KCL, so KCL we have already written. So in terms of the branch current equation, and then again we are substituting the KVL into this, and then finally it leads to this kind of equation: Yn, the node to node admittance matrix, Dn, nodal voltage into ISN. Okay, so in that way we have written. Now, if you are able to solve this equation, we can get all the node voltage. Once we get all the node voltage, we can get all the branch voltage. And once we get all the branch voltage, then we can get all the branch current using the branch equation. Okay, so this is the typical procedure of that. Now, what the problem is that you cannot incorporate a ideal voltage source. You cannot incorporate some kind of dependent source. Even incorporating the coupled inductor is difficult. So these are the various problem is associated with the conventional nodal analysis. So how to solve this problem? So the problem was earlier solved. Okay, so before the modified nodal analysis, that is basically tabular formulation. So in the tabular formulation, what do you do? We write down the KVL equation, KCL equation, and constitutive relationship. So instead of writing the branch equation only in terms of the branch voltage equation or branch current equation, we have generalized that. Okay, so this is the typical way of writing down the tabular formulation. Now, here any element can be written in terms of that. I'll discuss that, how we can write any kind of element, whether that is a voltage source, whether it is a current source, or it is any other sorts of source. Okay, so we can do that in that way, and then we can form that into a matrix equation. So this is a bigger matrix size. So we have a B plus B, 2B plus N. So basically, if you have thousands of branches, then you have a 2000, and then if you have again let's say 500 nodes and thing, so like that, it's basically become 2500 cross 2500 matrix. It's a bigger size matrix, and though it is a sparse matrix. Okay, so this is a very problematic thing to solve. Okay, if you have a large equation, matrix equation, it's very difficult to solve, and it's a more time consuming. Okay, now there is a way to reduce this further. I'll discuss that, reduce tabular formulation, and how do you write the constitutive relationship, okay, or constitutive equation. Now, for a resistor, we can write the branch voltage equals to branch voltage minus branch resistance into branch current is equals to 0. So here YB here is equals to 1 and ZB is equals to minus RB. Okay, and WB is equals to 0. And similarly, we can write it for a conductor, and we can write it for a capacitor, we can write it for an inductor, and so on. So for a voltage source, ideal voltage source also can be taken care into account. Okay, and ideal current source also can be taken care into account. So please note that this ZB is not in ideal sense, it's a ZB kind of thing. So maybe in other sense also it is used. Okay, for example, we say that YB of a voltage source is equals to 1. So it's not basically the admittance of the voltage source. Okay, so it's or that admittance of the particular resistance. Okay, so it's basically not in that sense, but to make it in a generalized way, we basically did it. Okay, so it's not physically indicate any kind of admittance. Okay, so this may be indicate a impedance, but this does not indicate like that. Okay, now we can do a reduced tabular formulation by just doing some sorts of manipulation in the equation, and then we finally reduce it to B plus N cross B plus N matrix. Okay, so this is your N number of nodal voltage and B number of branch current. Okay, so this still having some sorts of problem. Okay, so I don't need all the branch current to basically solve my initial equation. Okay, so what is the solution to that? The solution to this is basically modified node analysis. Okay, now the modified node analysis I'll discuss later. Before that, let's see that how the tabular formulation look like. Now this is an example of a tabular formulation. So here please note that in a conventional node analysis, this together I will consider a single branch, R2 and J1. But here in this case, this I have taken a separate branch. This is the current source, and this resistance as a separate branch, and these are the separate branches. Okay, so this is the one branch of this one, and then another branch of this one, G4. Okay, so these are 3 and 4 like that. Okay, and this is the incident matrix we have formed. And then if you write down the tabular formulation, it's a very big size of equation. Okay, and then if you try to solve it, so it is even though it's a very simple small circuit. Okay, only 2 node and we have 4 branch. Okay, so 2 node 4 branch. So what is that? So 4 branches, 4 into 2 is 8 plus 2. So basically 10. So 10 cross 10 matrix we need to solve. Okay, so it's a very big problem. It's a very big problem. And then we we don't like that kind of big problem, even though if we try to solve it using the reduced form. So in that case also we need 4 plus 2, 6, 6 you can say 6 unknown we need to solve. So that is also a problem. Okay. So what is the solution to this? The modified analysis. Okay. So in the modified analysis, what we do? So this is a you can say conceptual way of introducing, but we don't do this way. We don't form any kind of graph, or we don't write down the incident matrix in modified analysis. We basically use stamp that I will discuss later. Now, this is the conceptual way how the tabular formulation is modified into modified node analysis. Okay. So in the tabular formulation, if we break down your A matrix into two parts, so we have basically categorized the element into two groups. Okay. So one group that accept an admittance description, it is only having an admittance description, and another group which do not have any kind of admittance description. So in that case, we'll basically segregate into another group. So typically the inductor and the voltage source are the typical example, and some dependent source are also example. So we have categorized it into two parts, the A matrix equation or the KCL equation into two parts, and then we have segregated that, and then finally if we go and do some kind of algebraic manipulation, finally we get into this equation. So where your matrix size is n plus what about the m? So we say m are the current, unknown current we need to solve for. Okay, so m plus n, so n plus m, and m is much less than the b. So that's why it is the optimal way of solving the circuit equation in a general sense. Now, so typically we have to solve this equation, and once you solve this, so you can get the other branch, you can say currents and voltages. Okay, so this is the typical way of basically constructing the modified node analysis formulation. But please note that we don't do this formulation inside the computer. Okay, so what do we do? So we basically create stamps. So there are standard stamps are there for each voltage source and current source, and then based on the stamp we basically solve it. Okay. Now for a current source, the stamp is on the right hand side. You have minus j and j. So you have a jth node is there. So basically, please note that it's a node to node equation. Always note that it is a node to node. Okay. And some branches are there. Obviously, you have some branch current are there. So these are basically taken care by IB2. Okay. And not all the branch current. Okay. Now, in a node in node J and J prime, so there is a source is there, and from J it is going out, and into J it's coming in. So it's a negative and positive in the right hand side. And if you have a voltage source, so in between node J and J prime, so these are 0, but you have another thing is there, IE, the current going through the voltage source. This is another equation is there, and then we basically, if we write it in this format, so you have this node to node admittance matrix is 0, so this matrix elements are 1 and minus 1, and this is also 1 and minus 1, and this in the right hand side you have E, the voltage source. Now, similarly for an admittance, it's very easy to do. So admittance is basically Y and Y, and this non-diagonal element are minus Y, and right hand sides are 0. Okay. And similarly for impedance, we basically do like this. This admittance are 0, node to node admittance matrix is 0, and these are basically 1 minus 1, and this one is minus Z, and this is equals to 0. So this can be explicitly by writing down the your constitutive relationship inside your impedance or admittance, and then you can write this in this format. Okay, MNS stamp format. Similarly, capacitor having a particular stamp, and then inductor having a particular stamp. So these are the typical way of writing. And then if you have a voltage control current source, it is having a particular stamp is there. Okay, so in this way basically field. So depending upon if Yj equals to 0, if it is open circuit only, then in that case you can consider all are 0, only these elements are there. And in this way, this formulation continues. For a voltage control voltage source, you have another sorts of stamps. Okay, So every time you have a different kind of stamps are available. Okay, and please note that whenever we need to consider a particular uh, basically current, so according to the we extend that. Okay, so these are the current we need to involve. Okay, now this is another way of basically writing down the nodal equation. And so it's a 4-node formulation. Okay, you have another here we need to consider a current source. So it's basically, so 4 nodes are, these are the 2 nodes and these are the 2 nodes. Okay, so it's a 4-node problem or 2-port problem. And then you have current control current source and then current control voltage source. So these are the various. If you have an op amp, it's like this. If you have a coupled inductor or transformer, you have this kind of M&A formulation. And based on that, we basically do all the stuff. Okay. Now, why modified node analysis? So that is a very important question. Now, in case of you do a conventional node analysis, so B, P and Q, so you have a this one, the 2 nodes are there, P and Q, and P minus BQ is the VS. Okay, I don't know what is the current going through. That is the problem. Okay, and then if we consider an inductor, and so the voltage difference between the 2 nodes is basically DIL dt, and we don't know what is the basically the current. Okay, so the current in the left hand side we don't know, so that is the again problem. Okay, so these are the problem with the conventional node analysis. So that is basically solved using modified node analysis. And another important thing is that when we basically solve a transient equation problem, we basically break down the nodal analysis formula into 2 parts. Okay, one is basically your energy storage device. Okay, called capacitor and inductor. Okay, and you have a derivative of the nodal voltage and derivative of the branch current, or not all the branch current, only specific branch current which are required. Okay, and then this side you have the source. Okay, according to that we write down the source, and then we basically solve this equation. And so this equation is basically look like a state formulation, similar to some kind of state formulation, and then in a descriptor form. And then if we solve this using numerical technique, we can get all the node voltage and some branch current, and then from that we can get all the branch voltage and branch current. Now the M&A are basically for this is specifically used for a transient simulation. Okay, so you have a M and X dot is the unknown, and X is the unknown, and X dot is the derivative of the unknown, plus A into X is equals to BT. Okay, so as the time progresses, it changes in your time domain solution. Okay, and this A is the resistive part, so it is basically all the conductance of the resistance. Okay, and if you have the incident voltage source, okay, so these are the basically in the resistive part, and then in the reactive part you have the capacitance, you have inductance. Okay, and you have some 0 rows for the voltage source. Okay, now at a DC operating point, X dot is equals to 0, so capacitor becomes open circuit, inductor becomes short circuit, and the system reduced to X plus B, a simple equation. And for a AC or small signal, okay, and or a particular frequency, we can always write down this X dot is equals to J omega into X. Okay, and then A plus J omega into M into X, and this has become again a simple algebraic equation. So there is no differentiation is there. The differentiation operator is basically converted into an algebraic operator. Okay, so let's see an example of how this M&A basically look like. Now, in this example, we see we have a voltage source and one resistor is there, another resistor is there, one inductor, and then the capacitor is there. Okay, so we typically having a 3-node problem, and another is the return node or 0 node. Okay, the 0 potential. This is the node. Okay, we are not explicitly writing that. Okay, and unknowns are V1, V2, V3, and JVJL like that. And the system is basically of size 5 cross 5. Okay, so we have V1, V2, V3, these are the unknown. And what are the additional unknown? The current through this voltage source and the current through this inductor. So these are the two additional unknown as compared to the previous one. Okay. And so typical node analysis problem. Okay, so these are the additional unknown. Okay, because it is required. Without that, we cannot solve this problem. Okay, and please note that if I consider the same problem using reduced W also, how many branches are there? 1, 2, 3, 5 branches and 3 node 8. So 8 cross 8 problem. So that is reduced to 5 cross 5 problem. Okay, so this is the advantage of MNA over the W formulation or reduced W formulation. Now, what are the elements? Elements are this voltage source is V1 and 0, and this is R1 is V1 and V2 between the nodes, and then R2 is between V2 and 3, and L is V2 and 0, and C is between V3 and 0. So in that way, we say these are the branches, branch description, and these are the nodes are there. And then if we write down the KCL at V1, KCL at V2, and KCL at V3, then we can construct, and then if we write down the constant equation for the voltage source and constant equation for the current source. Okay, so in that case, we basically form this matrix equation, and if we are able to solve this matrix equation, we can get the basically resultant, you can say, voltage and current as they are varying with respect to the time. So please note that if you want to solve it in a for the DC case, so this term will go vanish, and then only you have to solve this equation. Okay. This is equals to 0. So this is the formulation for the under the DC condition. Now, if we try to solve it under the AC condition, okay, say a particular frequency is there in the voltage source. So basically, AC also we say a DC can also be said as an AC with a 0 frequency. In that sense, I can say, okay, and a AC signal, you have this additional term is there, and you will get a phasor relationship of the voltage V1, V2, V3, and this JV and JL. Once you get this one, then you can get all the branch voltage, branch current, whatever the things is required as per your requirement. Okay. Okay. Now, for a typical transient analysis, how do you solve this problem? Okay. Now, for a typical transient analysis, what do you do? We write down this MNA in this format. So you have a M x dot A x is equals to BT. Now, what we do? So this is the you can say differentiation operator. Okay, and we can do a numerical differentiation. Okay, so we can use the Newton forward or Newton backward difference, and according to that, we can do that. Okay, so you have initial guess, all the, let's say, voltage and currents are 0 maybe, or maybe you may have some kind of initial condition. This inductor and capacitor have some initial voltage or current. Okay, according to that, you have some initial conditions are there, and then you need to discretize this, and then you have to solve. So this become a linear equation. Okay, and then you solve this equation, and then again you store the value, okay, of the next iteration, and then you basically this loop continue, and in that way, for all the instant of time, you get the solution of the nodal voltage and some branch current. Which branch current? The voltage source and in the inductor typically, and other may also be involved depending upon the situation. Okay. Now, when it comes to the AC and small signal analysis, so in that case, you will have this sorts of formulation. You have this your frequency dependency, or basically the time dependency, basically reduced to e to the j omega t, and depending upon that, we solve all the quantity, all the nodal voltage, and then once we get all the nodal voltage for all the frequency, sometimes for some analysis you don't need all the frequency, only few frequencies are required, let's say 1 or 2, depending upon your problem specification. Okay, so let's say you're doing a typical AC analysis under the steady state condition. So in that case, only one frequency is enough, only source is there. Or if you have a 2 source, then you can make a superposition of that, and you can basically get the phasor relationship, and phasor relationship can be converted into time domain relationship. Now, these equations are basically sparse in nature. Okay, so you don't have all the elements are not filled, only few elements are filled. Okay, so depending upon the type of the solver and how we are solving that, so okay, so that the time basically depends upon the sparsity of that. And if it is a dense is not there, so mostly this M&M equation are sparse in nature. So therefore the time consumption or the basically the time complexity of the M&A equation relatively less as compared to solving a dense matrix equation. Now, this is a very important thing, and I want that all of you basically try to explore some kind of spice solver, like for example, NG Spice, which is basically freely available. As I know that eSim also use NG Spice in their backend. Okay, and this is the typical way of writing down the netlist. Okay, so you don't always need to build the wheel from the scratch. Sometimes you already have a good wheel, you can utilize it for your car. Okay, so that is the mostly recommendation we basically provide to the student. Okay, you don't always need to build the wheel from the scratch unless you are basically making a very innovative new type of design of the wheel. Okay, the same thing is applicable. This M&A is a very standard thing. Okay, and another important thing is that when it comes to some kind of complicated element, like if you have some kind of transistor description is there, some kind of diode description are there, so there are some kind of industry standard are there. So you can, for a simple
Hello, Professor
RC
Rakesh. Sorry to
yeah.
interrupt you. Someone is asking, Avinash is asking, what is N and M in your previous slides?
M&A.
N and M.
N, M, and where?
Where, Avinash?
M&A.
No, N and M.
Okay, small n and small m.
Yeah, small n and small m.
Small n is the number of node, and small m is basically is the branch where you need to solve the current.
Okay, thank you.
On not all the branch, all the B branch, only few branch are required. For example, where you have a voltage source or where you have some kind of inductor, typically. So these are the two kind of element where you need to consider the current.
Okay. Yeah, Avinash, I think this solves your query. Okay, thank you. Please continue.
Okay. So this is a very interesting thing, and this thing I basically recommend the student to do this one. So instead of directly, so it's fine initially when you are starting your career, you're drawing the circuit schematic, and then you are pressing the simulation button, and then you get the result. This gives more better intuition about how this workflow happen in a spice solver. Okay. So the thing is that we basically write down the netlist in the following format. Let's say you have the element name is there. Let's say this is V in some kind of voltage source, and that is between 1 and 0, and this is the AC source. Okay, and its amplitude is 1, and it is basically a sinusoidal source, and 10 is the, you can say, frequency. Okay, 0 is the phase and 1 is the amplitude. Okay, so in that way we can write, and then we have a resistance R. So please note that this is always a positive terminal and this is the negative terminal. So in that way, we basically, the inductor is connected between 2 and 3 node, and capacitor 3 and 0, resistor 2 is basically 3 and 0, and these are the values of that. And if you have a more complicated circuit, so it basically extend that. It's not, for example, if you have some kind of dependent source or something like that, or if you have a transistor or some other component. So depending upon that, so this netlist may extend, and this is very simple case I have shown. Okay, and then what are the kind of analysis you want to perform? Okay, so this is basically AC analysis if you want to perform. So from 100 to this 1 megahertz, and then if you want to perform a transient analysis from 1 microsecond to 500 microsecond. Okay, and then if you want to measure some kind of you can say 3 dB bandwidth, so you can write down like that. Okay, if you basically want to plot the V3 in dB, so the nodal voltage at the third node, so you can plot like this. Okay, so this is the command is used typically spice solver. Okay, and So these are the typical way of writing down any netlist, and then how the netlist is processed inside the you can say this solver, or the spice solver. Okay, so you have a netlist. Okay, so or the .cir or .sp. So this is the specification of that, and then you basically tokenize that and text into your token, and then you use the parser. So element list, what are the elements are there, you create the stamp for them. So you basically create the A matrix and B matrix, and then use some kind of sorts of solver. Okay, and then in that way you basically get all the desired branch voltage and branch current, and whatever the thing is required. Sometimes you have seen that you have connect some kind of voltmeter or ammeter, and then you check the reading, or sometimes you connect some kind of oscilloscope in your simulation, and then you check that. But inside that there's no oscilloscope is there, nothing, everything is virtual. Okay, so everything is, so basically in the end of the day we basically solve the MN equation, and then we get all the node voltage and node current, and then basically whatever thing is required, and then that is basically displayed into your simulation plot. Now if you put all together, so you have a spice net list. Okay, and then you have a parser. So you have this MN stamp is created, and if you have a DC operating point problem, okay, so you basically AX plus B, this problem is solved. If you have a AC switch, or basically a single AC also may be there. Okay, a particular AC frequency point you are basically, for example, you are simulating for a particular AC circuit in a steady state condition, you basically go for this one. And in the most of the cases we basically do a transient simulation. If you have a nonlinear element, then we basically use Newton-Raphson for basically linearize the nonlinearity. And then if you use some kind of solver, we basically use, okay, and we basically LU solver, or say, let's say QR decomposition, or there are other solver also there. Okay, so or you simply use some Gauss elimination to solve this problem. Okay, or some other advanced level solver you can use to solve that. And then you get the node voltage, some node voltage, and the branch current. Not only the branch currents, few branch current, and then from that you can get all the branch voltage, branch current, power, whatever the things you want to do, you can do some kind of post processing. Okay, so your final thing is, your initial thing is that all the node voltage except that your ground potential, that is basically already zero, and rest of the thing you get. And then there are certain kinds, this thing I don't need to discuss. Okay, so what are the typical spice solver are available? So these are the spice solver available. So you have a ngSpice, that is open source, so I will recommend you can explore. And if you face it's a little bit difficult thing, you can start with PySpice. So that is basically PySpice basically call ngSpice inside it. Okay, or you can another library is there, LCAPI. So that is only specifically for the linear problem. Okay, well, there you cannot get a nonlinear problem, you cannot solve. And LCAPI, so that is basically linear something is related to that. Okay, linear circuit analysis, PY is for PY is for Python. Okay, then you have a LT Spice is there, then Joyce is the H Spice is there, and you have a Siemens EDA is there, you have a Cadence EDA is there. Okay, so these are the various EDA tools are available. So all are basically depends upon this core concept called MNA. Okay, MNA is the core, and based on that, all the basically solver perform some kind of analysis. Okay, I'll show you some small demo, like how this netlist processing is done. Just a minute. Okay, so a typical net list here we have seen here. Okay, so you have a voltage source that is between node 1 and 0. So you can imagine that, or you can draw it by yourself. Okay, and then you have a R1, one resistance is there. So that is between 1 and 2. Okay, and then you have another resistor R2, that is 2 and 3. And then you have another resistor that is 3 and 0. And this problem, if you try to solve, okay, so let's see that how it should look like. It's taking some time to choose the. Okay, so it's basically showing the results. Okay, so what is that? Node 1 having a voltage of 1000 volt, and this is having 6000 and so on. Okay, so these are the voltages it is having. Okay, and similarly the voltage across your V1 is 1000, and then current through V1 is equals to minus 2 ampere, and so on. The voltage across the resistance is basically 4000, and then current through it is basically 2 ampere, and so on. Okay. So according to that, it's basically automatically solve the problem. I don't need to write down the explicitly my KCL, KVL, or any sorts of like you can say I'm actually solving the node analysis problem, but I'm not using any pen and paper. So it is automatically done through a particular solver or engine, okay, a spice engine. Okay, so this is the typical flow of solving any kind of circuit analysis problem, and most of the solvers are basically depends upon the standard M&A formulation. Okay, so
Yeah.
okay, okay. So I basically conclude here. I'm not discussing further regarding this topic. And from the students, if they have any question and query, they can ask. And if they are interested in some sorts of this M&A, exploring the M&A and doing to write their own script to solve some sorts of circuit related problem, they can do. And I will recommend that you can go to the ngSpice website. So there are some kind of easy steps are there, and one of the most preferable way of using ngSpice in the Linux environment, that is better, it works better compared to the Windows environment. And yeah, so you can start exploring, and then once you start exploring, then you will learn more. Okay, with a one lecture you cannot learn all the stuff. It takes some time. Okay, thank you.
Yeah, thank you, Professor Rakesh, for the insightful talk. And perhaps after your talk, many people will come up with their own simulators. The Python thing which you have shown was wonderful, and the slides and everything was great. So, any questions from the audience? Attendance link maybe we will share, but any question? So it's a wonderful thing to know about how Spice works internally, and yeah. So as Professor Rakesh Sinha said, it's a great experience looking into the Spice manual and trying out various fancy things. So
Yeah, even this keycat they use also ngSpice in the
correct,
backend.
yeah,
Yeah, even eSIM also, I think they also use ngSpice in the backend in somehow.
yeah, yeah. eSIM uses Spice, and we have integrated it with GSDL and Verilator, so it has
Ah.
the mixed signal simulation feature as well.
Yes, 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 yes.
So Yeah. So anyone, any questions? How to do Python code for circuit and which tool perform?
So
Aditya Mandal
initially,
is
you
asking.
can start with LCAPI or PySpice, and then gradually move to ngSpice. So that is my recommendation. Okay.
Okay. Yeah. Thank you, Professor Rakesh. I mean, it's pretty much straightforward. You can import PySpice and try it out.
Yeah, yeah.
Yeah. Anyone else? Anything? Is it same like electronic design automation, sir?
No,
Shavali is
the
asking.
total flow is called electronic design automation. So simulation is a part of the electronic design automation. Okay, so it involves many things. Okay, the designing part is also involved. Okay, and yeah, you can do some sorts of things. So if you have a particular design is there, if you want to do the circuit simulation part, you can use the ngSpice or some other spice. Okay, so that is the circuit simulation part. And not only that, you also need some kind of full wave simulator to do basically parasitic extraction and things. So this basically beyond the scope of this lecture.
Yeah. Thanks, Professor Rakesh. Anyone else? What? These are free tools.
Yes,
PySpice.
yes, yes. Spice is free, and this LCAP is also free. And what we are developing, circuit sim, that is also free. Actually, we have a limitation in budget, and sometimes we basically turn on our solver, and sometimes we don't. So depend. We are basically in a development stage, not fully developed. Maybe in future, if we launch some kind of startup, then we obviously we will try to make it available to all the participants.
Okay. Dr. Rupa is asking, can we get the complete flow of the design with the tools?
Yeah,
So,
complete flow means so, so basically I have shown that how this thing work in internally. Okay, so there are various levels of simulation. For example, let's say if you are designing something in let's say digital circuit you are designing, so inside that you have some lots of transistors are there, so that this problem again solved by M&A only.
and I would like to, Professor Dr. Rupa's question that I would like to add to whatever Dr. Rakesh, Professor Rakesh said. Yeah, so the complete flow from the eSIM, you can do it. We have digital, so simulation wise, everything is available on eSIM, digital, analog, and everything. After that, you can go ahead with the open road, Yosis for synthesis, and Yosis for synthesis, and open road for complete RTL to GDH2. We are integrating them as well in the tool, in our tool chain. So hopefully, sometime we will have the complete flow ready, and in the upcoming next FDP, maybe after a few months, you will have the complete. We will have the complete flow FDP on complete flow. Okay. Anyone else? Any other query? Sir, I am working in Vivado, but simulation part is limited. Professor Rakesh?
No, actually I cannot comment on that. Okay, so basically I am not very expertise with Vivado and thing. Okay, so I cannot comment on that. Okay, so mostly that analog part and RF part, I'm basically having idea that how these things works. Okay, and based on that, if you have any query related to that, I can talk about.
Yeah. And that's why we are promoting open source tools. As Professor Rakesh said, Vivado is a proprietary thing. So you should try open source tools. You will have a lot of freedom. Nothing will be limited to you. And we are there to help you. So can you please share the link of the EDA tool used in your session today, Professor Rakesh?
Okay, I'll share this one. So uh, currently, I have shown you that circuit sim that actually we have developed by some undergraduate student and another intern. Okay, he is actively working in this work. Currently, that intern is working, and yeah. So I'll share. Definitely, I'll share. So for the timing, it is in the development stage. So I don't want that it should be that the website get loaded with lots of traffic. Okay, for the timing. So once we get launched this software. Obviously, we have some different plan that we will not use some conventional solver in future. Maybe some kind of new solver will develop, and yeah. So that time obviously we'll share that. Okay.
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 Um, One question to me, Sumanto, can we use eSIM for signal analysis in communication system? So eSIM directly doesn't have signal analysis things, but yeah, you can do it. But ngSpice does support, so you can design the schematic in eSIM, and you can manually edit the netlist file according to your convenience, and do whatever Fourier transform, FFT, and whatever you want. And I hope this answers your query, Vivek. Vivek Kushwa. Which tool provides optimization for designing the CNN processor using Python? Professor Rakesh?
What is the question?
Ramalinga is asking which tool provides optimization for designing the CNN processor?
That I
CNN
cannot
processor.
I cannot comment on that. I don't have any idea.
Hmm. This is a difficult question for me as well. CNN processor is a very big thing, but can you suggest some parts of the processor? Maybe some blocks.
No, no, I'm not expertise in the digital design part, so I should not comment on that.
Yeah. Okay. Ramalinga, can you suggest some blocks of the processor maybe so that I can answer at least. Check is okay. HOD HRIT is asking, please share your email. Would you like to share your email ID, Professor
Yes,
Rakesh?
yes, no issue.
Please share it over the chat box.
Okay.
Okay. Can we do complete simulation with hybrid components in mixed model styles? Hybrid in the sense analog plus digital. If it's analog plus digital, yes, that can be done in eSIM, and Spice will do the
Yeah,
implement
and
the
then
MNA
even in
and
NG Spice,
do
this kind
analog.
of option is there, as I know.
Yeah. How does Spice convert a circuit schematic into a system of equations using MNA? How
Yeah,
are
that
linear
actually I will
devices
discuss.
like diodes and MOSFETs incorporated into the MNA matrix?
Yeah, very good question. So nonlinear are basically treated as a linear component. So they do some kind of linearization at each every timestamp or time steps, and using that they basically solve a linear equation. Nonlinear equation you cannot directly solve, so that nonlinear equation is converted into some kind of linear equation, and then it is solving. So there are numerical techniques are available.
Okay. Where can we read about MNA basics?
That is a very good question. I have not shared that slide. Okay. So one good book is there. That is, let me check that. There's a book is named Computer Method for Circuit Analysis and Design by Walsh and Singal. That book you can start with, and then obviously once you start with, you can get your own resource.
Another question is, yeah, you can share the link or whatever the name in the chat box, maybe Professor Rakesh. That will be helpful for the participants.
Okay, I can send the book name.
Another question from Dr. Rupa, sir. We use eSIM for analog mixed mode designs. Yes, you can use eSIM for analog and mixed signal designs. Um, uh, Dr. Ponlatha is asking, I am working on FinFET for noise cancellation, but power reduction is a tedious process in cadence. Can you please give input regarding this?
Okay, what is the question?
I am working on FinFET for noise cancellation, but power reduction is a tedious process in cadence. Could you please give input regarding this?
Uh, no, I cannot comment on that. I am not working in the device level, so I basically work in the modeling part.
Mhm. So, yeah, I mean, NGSpice has lots of options. You can try it out as I said, by
No,
playing
no, that is
installation
mostly
and
it is a circuit solver.
device.
If you want to solve this
Device
fin
as well.
fed from the physics perspective, it is solve basically Poisson equation.
Correct,
And
correct.
so there are basically specific softwares are available. For example, TCAD and some other softwares are available. They
Yeah,
basically solve that basically Poisson equation, and then they basically get that voltage current relationship and then other parameters and things. So
yeah.
basically, it's a full basically electromagnetic simulations rather than the basically simple circuit simulation.
So,
So mostly this spice are mostly circuit simulator, and the electromagnetic simulator and the physics-based simulators are a little bit different. And there is a interchange between them. We basically do like that. From one we get some data, and then another that
yeah.
back and forth.
Yeah, definitely. TCAD is one of the tools, but TCAD is proprietary. But
Yeah, ticket
yeah,
is
there
proprietary.
can be some workaround that can be done. You can refer
Maybe
to
I'm,
the
I'm not sure.
papers
Maybe there are some
to
tools available.
work with FinFET with NGSpice and eSIM. You can try out. You can refer
No,
to some papers.
NG Spice will not give that one. Basically, NG Spice, what they do, they already have some inbuilt. Let's say if you have a particular PDK model or thing, so they all someone already have perform all the steps, and based on that, they basically characterize the transistor and things. So and you will get the basically circuit model out of that. It's not actual physics solving of the thing it is doing.
Yeah, okay. Then can you suggest? Can you give suggestions on memory optimization? This is something off topic,
No,
maybe.
no, of the bit.
And sir, I am working on hybrid agricultural system. Any tool for this complete model can be simulated together. Again, something
That is beyond my scope, but
beyond our
obviously
scope. Yeah.
if you're able to search something, you will get obviously some work. Or
Uh,
obviously, or there are always some kind of open source work out there. But one of the thing with the open source is that they are not always easy to use. That is my experience. Okay, and most of the people are also experience like that. Because that are mostly designed for the developer, those who understand the thing. Okay, and another thing is that most of the commercial player what they offer they basically easy to use. Okay, and the resource and the manpower and the basically economic constants are there in open source development. You may not get a good amount of funding for open source development as compared to a commercial development. So these are the some of the restrictions are there. And obviously you will able to get some sorts of tool is there you will get. But one thing is that if you want to explore open source, you should have a time to do so. Otherwise, if you want to get immediate solution, you need to go for the commercial one.
mhm. Yes, but eventually, one after one gets hands-on with the open source thing,
Yeah,
hands-on
it
on
is
the
it is
open
getting
thing,
better,
it actually
but
feels that. I want to talk about the
it is
time.
getting better, but it takes time.
Yeah, yeah. Another question is, we may change materials using PySpice or other tools.
No, 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 no. It's a circuit simulator. You do need to understand the difference between that. Okay.
Yeah.
So it is a circuit simulator. If you already have some kind of model is there inside the PySpice, you can use that. Okay, so there is a difference between circuit solver and then EM solver. Okay, so that you need to understand. So material property and things, that is basically comes under the physics solving, and under the circuit solving, this ngSpice and thing, they basically do that part.
Mhm. Yeah, any more questions? Any more question? Any more queries? Book name, huh? You didn't give
Ah,
the. Please type in
I'll
over here.
provide.
Okay, any more questions? Anyone? I guess everything is done. Okay, so I would like to thank you again, Professor Rakesh, for giving me time for this session. And yeah, it was very much enriching to know about modified nodal analysis and a lot of insights about spice
Okay,
simulation.
okay. If another thing is that if
Thanks.
anyone is working in RF and RF design and things, so basically the circuit level, I have developed some softwares, me and my students. Okay, so I'll send you the link. Okay, you can go and download that, and you can use it for free. Okay, so but it's not open source; it's a closed source, but the freely accessible.
Okay. Okay. Thank you, Professor Rakesh.
Thank you.
Then moving on to the next session. So Ms. Santipriya will be demonstrating some nodal analysis using eSim, and it's a hands-on session, and she's between the lunch and yeah. So have some patience and listen to her for the next session. And yeah, we had a wonderful session yesterday by her on FPGA on simulating using ngVary feature of eSIM. So we will be now. She will now demonstrate running a simple nodal analysis circuit using eSIM. So what do you, Shanti?
Yeah. Thank you, Sumantha sir. Hope my audio is clear to everyone.
Yeah, it's clear.
Yeah. Thank you, sir. Yeah. Let's do hands-on on eSIM. I'll show you how to design a simple circuit in eSIM and how to verify its node voltage for nodal analysis. Let me share my screen.
Yeah, your screen is visible.
Yeah. Thank you, sir. Uh, we need to create a project. Let's name it, and now double click on it. Open the schematic editor, and if anyone is following to me, you can follow. Like I'll do it slow. Fine. Now create the schematic editor. Now for a basic analysis, we can take a source. Click on the components list. Just a minute. It will take some time. I think it's visible now. So let's take a source. To rotate the components, you can click R and place it over there. Again, let's take another resistor. I may have to need a ground. Yeah. And for wiring, you can click W. Take care of wiring the components perfectly. Yeah, hope it's visible to everyone. If you want, you can take screenshot and try other in some other time. As it is a DC source, we can give the value here itself by clicking right click. There, just a minute. Yeah. For giving value, you can press V also. Let's say value 10, and for resistor, you can take 5 ohms, and for this you can take 5 ohms. Let's say this has 4, and let's take 20 for this. Yeah, hope I gave every value of the components. Now save the circuit by Control S and go to the file, export. There you will get the test option. Click on it, navigate to Spice tab, click on the checkbox and export netlist. Save the .circuit file. As we didn't done the annotate, so it was showing annotate, so click on annotate. Now it was done. Go back to the GUI of main window of eSim. Now click on Kick Add to ngSpice. Now we will get the options for timing analysis.
Yeah, so you
Let's
can close this window. This PIP window you can close.
yeah. Let's give 9 seconds. Yeah, and we already gave source details and nothing is there, so directly click on convert. It will ask you, it will say it was done successfully, and next navigate to the button simulate. Yes, yeah, now we'll get the in the spice plots. Okay, as we didn't name the labs, it was showing as a branch. I'll show you. There is an option for labeling. If you click on it, let's say it as VA. Let's call it as node VA, and sorry, call it as VP. See, as we are checking the node values, we are labeling the nodes. Now save the file. Again, back to the window. Everything was done. So simulate it again. Yes, it will show the node names. If you click on VA, it will give you around 10 volts. VP, VC. But if you want exact values, you can click on multimeter so that it will show the exact volts. So yeah, let me show you what was done. Yeah, if you didn't follow previously, you can again follow me along with the PPT. As we open eSim, we created a schematic using schematic editor and save the file, export the netlist, and after that we are giving timing analysis here and clicking on convert, then go to simulate. It will give you in spice plots. As how we got the same screenshot I kept here. And for verification, as you already know, if we done the KCL on this, it will give you the exact values like 10.77, as we already got the same result. Yeah. If you have any doubts, then we can discuss.
Sonia is asking what after the schematic is being saved.
Your schematic file is saved. Whatever you designed in the schematic, that file is saved. Is it fine, Sonia?
You can share the netlist and you can share the screen and maybe show the contents of the schematic. Share the steps again, basically.
Okay, okay.
Show the steps once again.
Yeah. We created a project and we open the schematic. Yeah. We have to design everything. Hope you are not confused with the components. Save this file, clicking Ctrl plus S so that you can't lose your schematic even if your system was closed. After that, you have to click on File. There is an option called Export. Under that, there is another option Netlist. You can click on it. Now try to navigate to Spice. Click on the checkbox. Export Netlist. That will create a netlist and you have to save that file. Once it was done, it will ask you annotate. It, uh, if you already done, it won't ask. If it isn't done, it will ask you. The annotate option is under tools, annotate schematic. If you click on it, annotate. Then after, we have to go back to the main window. Click on KiCad to in the spice option and give the timing analysis. Start time 0, step time, stop time. If you have sources, already we have sources, but we gave the details inside the schematic, so it's not showing it here. If you didn't give there, it will show here. You have to enter the source details. Once you done, you have to convert, and it will convert the KiCad to Spice successfully. Click on OK and simulate it again, and it will ask you for Spice plots. Click on S. Yeah, it will give you the UI, and whatever the plot you want, you can click on the checkbox. You can plot. If you want current, if you want to check the current, you have to take a component plot V2
Hello, Shanti. Hello, am I audible, Deepak?
Yeah.
I guess some issue from Shanti.
Yeah, the laptop is little low charging. She's connecting.
Okay.
Actually, Shanti won't be continued just because her laptop accidentally crashed and it's not opening now. So, any questions from the participants?
Okay, I will show them sometime something. Just give me 2 minutes.
Yeah, and
And
one question was there from last meeting that also I need to address. So, just after you, I will do.
okay, any questions until then? Maybe Bharat can answer. Let's set up something.
Yeah. So yesterday someone asked related to the IV characteristics of a diodes, and as I said yesterday only that yesterday there was little less participants in the evening session, so I said we'll do it today. So we have some time today. So what I will do, like as everyone has installed eSIM in their laptop, so as everyone know in the for C and eSIM folder we have some examples. So within example, there are some good examples to check the voltage sweep of the voltage sweep, and if we want to do AC analysis, DC analysis, and transient analysis, they're like the three basic basic analysis thing that you can do on eSIM. So yeah, once sir has done with their thing, I will be continuing. How can I watch yesterday's class of Steve? Yeah, it is actually recorded well. We have the recording session with us. We will be shortly uploading on YouTube, and we will get the link maybe up to the today's last session in afternoon. We'll share it. So Deepak sir, you may please check it.
Thank you.
Yeah.
Hello, am I audible?
Yeah.
Just a moment. Yeah. So since we have some time, so I will be continuing with the, I hope my screen is visible.
Yes, yes.
Yeah. So I'm just creating a new project on MNA. Sorry, not, I will just name it as NA. And we'll create a random circuit. By the way, I'm on uh, Linux system. So register. Okay, and I'm just connecting a DC source. Sorry. So this is a random circuit I'm drawing. Also adding the ground somewhere strange place. Okay, and let's analyze this. We need to give the register values. So let's make it a bit interactive maybe. So can you suggest some register values in the chat? Okay, 2K. Okay, some other people, can you suggest some values here? 10K, 50K, nice. Okay, okay, R7 maybe 1K, okay. R7, okay. And 10K. Excuse me, did it close? Oh, let me see if. Oh, it got closed, sorry. Let me draw it again. Yeah, but I will note your values. mistakenly clicked on the close button. So, we can even add dependent sources, but for now we are playing with only the independent ones. What values did you suggest? 50K, 2K, 50K. 2K, 50K, 10K, R2S, R7S, 1K. R7 various R7. Let me annotate it. Annotate, yeah. R7 is 1K. 1K, then R2S 3K. Any more values that you want to suggest? R2S 3.3K. Okay. Any more values? This is the schematic. We have R8, R3, R5. R8 5K. Okay. R3 4 5.1. R8 is 5K. R3 5.1. R5 anyone? R5 is 2K. Okay. And R6? R6 10K. Okay. Nice. Now I can see Sonia uh, messaging every time. So it will be great if someone else also says about the values for DC sources. Suggest some value from DC sources. Anyone else? DC sources values. Anyone? 10 volt? All 10. Okay, 15, 10, 25. Nice. Since I'm in Ubuntu with the latest version, I'm not exporting the netlist. Other people need to do it. There's a connection remaining. Please note these green dots are junctions, while if you have red boxes, unfilled boxes, then small boxes, then those are not connected wires. So beware of the connections. For now, it's good to go. So yeah. So now let's refresh it. So we have the following files. Let's do keycat to ngspice 0, 1, 100. Okay. Everything, nothing else is there. Clicking on the convert button. Okay. And yeah, let's now run the simulation. So all the nets, we didn't name the branches. We can name them. So maybe let's name some of the nodes. Suppose V1, V2, V3, V4, V5. Okay, now redoing the things. Where there was some issue. Yeah, this is fine. Saving it again. V1, V2, V3, V4, V5. Okay. This is ground actually. Let me delete it. Yeah. Check now. So it says some singular matrix. Check nodes V3. Let's see what's the issue in V3. Yeah, V3 is also actually ground, so no need to name it. Instead, huh. So this way one needs to check every time whenever he or she is playing around with spice. So we cannot rename the ground. Uh, and problem with V4 as well. V4 is also a ground. We cannot do it. Okay. So yeah. So one cannot rename ground. V5 one can do. V6 over here. Okay, let me try something even more complex. Maybe I will add a bridge kind of over this. Yeah, now it looks great. I'll have something over here as well. Okay, I'm saving it. And convert. Okay, you want plots? Yes. Still, it's showing some errors. Add V3. Can anyone suggest something? Why it may be an error? Why it may be causing an error? Let me do the conversion once again. Some issue at V3, it's still there. Yeah, can someone help me debug this error? So two independent sources are coming in parallel, kind of. So that is an error. Yes, let me delete this component. Yeah. Yeah, now it's working. V1, V5. So V5 is 0 and V1 is 25. There is V1, this is V1. So let's add some more labels. Maybe V2, V5. Yeah. Let's rename this one maybe. convert and run simulation. Yes. Okay, VAVB and select all. Okay, I can plot from this electricity law. Let me check. Convert. Okay. Okay, from the ngSpice windows itself, we can plot the other things maybe. Plot VA. Yeah, you see, no, VB. This is not there. Sorry, the plot didn't generate this. Let me check the schematic file. This once. Okay. Sorry. VA is already VC. So again, like me, just take care while naming it. Yeah. PD is connected to this one. And if no current is flowing, then no VD. Okay, so 25 and 0 for BB. Let me change it a bit again. Maybe delete these nodes. Okay, now this will act as short. I will delete. Just in the matter of doing the things randomly, I have added everything else. Yes. Yeah, now VD has also come. So VD, VA, and yeah. Now different. So maybe some other node. Maybe I will connect this. Or add a register over here. Saving it. Going back to eSIM and converting again. Simulating. Okay, so minus 3.9 was the earlier value. Now it's minus 5. Okay, VB has changed to around this. It's around less than 15 volts. Around, you can have the plot here. VB is 14.5 and VA is now minus 10.5 volts. Here you can see the values. Okay, now, yeah, so you can even check the currents over this. We can even do the DC analysis if you want. So let's take V1, start 0, increment as 0.01, and stop maybe 10 volts. Okay, convert. Yes. Okay, so the sweep values are available for you. So you can see the changing values, the slope of different. Okay. Okay, and yeah, so this is one of the things which I've shown. Again, in this spice manual, you will see a lot of things available. So, which Professor Rakesh was saying. So, yeah, so .op is the current one. So using .op, you can find the operating point and point values. So in this itself, if you do .op, sorry, it's .op and run the simulations. Yeah, dot control. After that, before running, just try yeah .op here. 7 exit. See, yes. Yeah, you can check the exact syntax. So you will get the operating point values of the uh, different DC analysis for you can do the node and you can get the node voltages at the operating point. Okay, and yeah, so transient is obviously there. And you can yes, someone was asking about small signal analysis, so you can do it using this. And yeah, you can refer to the ngSpice manual. I will share this link in the chat. Okay, so a lot of things can be explored over here: sensitivity analysis, noise analysis, and a lot of things. You can just from eSIM you can just edit this. So we are offering AC, DC, and transient. In future, we are also planning to have frequency, other things, noise analysis and all. But nevertheless, you can go and edit the .ci.out file and add whichever analysis you want to add. Okay. So .op for it. I don't remember the exact syntax, but you can check .op how to do it. Okay, and yeah. So here are the list of the syntaxes: .commands, .ac, .control, .dc, distortion analysis, else if, and so on. Okay. Yeah, I would also like to show you something on the eSIM. Yeah, so we also have this cloud version of eSIM. I will share the link over here in the chat and pin it. Yeah, meanwhile, let it load for some time. And meanwhile, do you have any queries on this, whatever I've shown? Maybe this circuit can be one of your assignments. You can go home and analytically try it out and check whether the values are matching. So current values, what we get? Uh, Maybe back to transient. Yeah. So minus 5.26 and 14.5 and minus 10.5. So just take a screenshot of this and try it out at your free time and check whether analytically the values are matching or not using KCL, KVL, and other nodal analysis rules. Okay. And maybe you can give this assignment to your students. Yeah, anything from your side? Hello, participants. Any queries, any doubts until now? Hello, are you all awake or waiting for the lunch? Okay, I'm sharing the screen once again and I will show you the EDA thing. Yeah, this is the EDA schematic, EDA tool, sorry, cloud tool. So earlier we talked about eSIM on cloud development. So this is the schematic. This is the front end. We are improving this. Many of the interns are working heavily on this. So as of now, we support. So there's a gallery where you can get the sample schematics, sample circuits. So for example, we can take which one to take. Anyone? Please comment something on the chat box. Hello all. Multi-vibrator. Okay, which tone? Okay. Okay, let me try then which tone since it also matches with nodal analysis. So yeah, so we can see the resistors, DC sources. Let's check the resistor values. 1 ohm. Okay, so yeah, so let me simulate. So DC solver, run DC solver. So yeah, you got the values. So 5 volts, 1 1 0 1 1. So this is 0. So yeah. Yeah, this is the value set. This is the plot output of the DC solver at different nodes. Okay, so we are improving this UI also so that one can view it side by side, um, and check the schematic. Okay, and someone told stable multi-vibrator. Okay, let me check. Stable. So yeah, so this, and let me have some start time. Maybe I don't know. I am trying this circuit for the first time, maybe, or I did it some time back. So I don't know what values to be given. Let's try. Eh, yeah, so the resistor value is in 1K and capacitor in 18 micro. So what should be the range? Can anyone say of the transient analysis? What should be the time period and the step time? Obviously the stop time I'm saying. For how much time should I run? Okay, let's give it as 1 second itself. And stop time. Sorry, stop time as step time as 0.1 milli and stop time as 1 second. Now let's try. It will take some time. I did a very small value. Um, don't give so much small. This is also give it a bigger value since it's on cloud, so it communicates with the backend and gives the output. So just give bigger values, not smaller ones. 1 and 10 milli. Okay, so yeah, I mean this is the output. As you can see, it's not multi-vibrating, but you can play around with the register values and get the actual plot. You can even add the model transistors, whichever you want to. And if you have some expression, you can add multiplicity factor and so on. Okay. So other things you can modify. Someone asked for a RC circuit. So let me open up the RC circuit. So this is the RC circuit. This is the sine wave. And let me simulate a transient. So let me check the values. So yeah, so frequency is around 200 hertz. So 200 hertz in the sense 1 by 200 is around. We'll take something in milliseconds. 10 milli. And check the use initial conditions box. Yeah, so you can see the output and calculate the phase difference at every point, every node. Okay, so this is our C parallel circuit. Yeah, I mean you can try out. Okay, someone suggested 5 milliseconds. Yeah, but these values are not tuned. You can tune the values and try out and do an assignment for the stable multiplier. Okay. Anything else you want to suggest? Say like, yep, yeah. Hello all. Are you there? Any doubts, queries? Hungry for lunch or like waiting for lunch? Okay, I can see some thumbs up. Nice. Okay. Okay, we'll practice then comment. Sure. If anything, just let us know. We're happy to hear. Can we perform neuron in this tool? No. Neuron, it's not an ML tool, it's a circuit simulation tool. No. Neuromorphic, no. Yeah, if you have the models, spice models equivalent to for neuromorphic design, then you can try it out. Uh, but yeah, not, it's basically spice. So yeah, there are various papers where you can try neuromorphic. CMOS neuron, yeah, CMOS neuron. You can, yeah, Giridhari, Mr. Giridhari. You were asking something, Professor Giridhari? Okay. Okay, then thank you for joining. Bharat wanted to say something, I guess. If you have any doubts, just feel free to message here. And that's for some time. Let Bharat talk for some time, and then we will go for lunch. We will come back around 2:15. Uh, okay.
Yeah.
Thank you. Thank you for
So
joining.
thank you so much,
See
sir,
you
for
again.
the
See you again in the
nice.
afternoon session. Okay.
Yeah. Thank you so much, Sumantakar, sir. And as I said, like for that yesterday's thing, we have some more time in the afternoon. Like we have one beautiful session from schematic to silicon, exploring Sky 130 PDK with eSim from Vipul Sharma, who is the founder of Navia Labs and former scientist at SCL Chandigarh. So what we will do just after the session, we'll be having one hands-on session on Sky 130 by Miss Shantipriya, and then we will follow it. Yeah, join at 2:15. Yeah, and then we will do some different analysis like AC, DC, and transient. Transient we already did yesterday. Only I just wanna show the AC and DC to like yesterday someone asked for the IV characteristics of a diode that I will show, and that is one good thing that everyone has that example in their laptop. Just because when we install eSIM, when we download the eSIM, these predefined examples are there. So we will look into that, and I will show some more thing. So yeah, for now it is done from my end. Deepak sir, you can keep that lunch break screen and timer. You can take to uh, 2 2 p.m.
Okay, Bharat.
Yeah,
2 or
thank you
2:15.
everyone. Yeah, we will put it as the 2, and we may start at 2:15.
Okay.
Yeah, or 2:15 is also fine. Nothing to worry.
Yeah.
You may keep 2:15 only then.
Okay.
Yeah. Okay, everyone. Thank you so much. We'll meet
Thank
you
you.
after the lunch.
YouTube link you want? Bharat, will you
Yeah,
share
yeah, I
that?
will send. Yeah, yeah, I have. So for the YouTube link, I'm sharing three links to everyone. That one is the YouTube live link. Whenever you click on that, it will directly take you the live session. And one is the all streams. When you click on that, you will get all of the session. Even though for the tomorrow session link is also there in all streams. And particularly to the evening session, you will yet to upload. Will upload and get to you all. Okay, I will
Yeah.
just pin it here.
And subscribe to the Fossey page.
Yeah,
YouTube.
do subscribe to the Fossey, share, and feel free to comment on that. We will really appreciate your comments and appreciation.
Yep. Thank you. Bye. See you in the afternoon session. Hello. Yeah, we will start in 1 or 2 minutes. Am I audible, Deepak?
Yes, Sumanta.
Varad?
Yes, Sumanta, you are audible.
Yes, yes, sir.
Oh, sorry. I didn't turn on my mic. Extremely sorry. Yeah, so welcome to the FDP program. Am I audible?
Yes, Sumanta.
Yeah. Welcome to the FDP program on VLSI Design using eSim and Open PDKs. So this is the third day. So this is the afternoon session. And as per the schedule, Vipul Sharma will be talking on free schematic to silicon, exploring Sky 130 PDK with eSim. And after that, we will have a hands-on session of Sky 130 PDK with eSim by Miss Santipriya. So introducing Vipul, so he will be talking on from schematic to silicon, exploring Sky 130 PDK with eSim. And introducing Vipul, he has worked as he was a he's the co-founder and analog RFIC design lead at Navia Labs, and he has 22 more than 22 years of experience in Indian semiconductor industry, and he has worked as a scientist at SCL Chandigarh, Mohali, which is under Department of Space, ISRO, and he has also worked with Navik team for the front end RFIC design, RF design, ASIC design, and he has also worked on different PDKs, including Sky 130, GF 180, ISP 130, and he has also sent. He was one of the marathon winners of last time the ISP 2025 hackathon marathon, which we conducted in November 2025. So he was one of the winners, and he has also sent an design for fabrication, and hopefully it will be there soon and fabricated soon. And he is also engaged with the IEEE, and he is one of the leading technical committees in Chipathon, IEEE Chipathon, and recently he also organized a boot camp along with FOSSI for learning about different design flows. Okay, VLSI design flows. So this will be a very enriching session from a very experienced person in industry, and lot of things we will be able to know from him. So happy to have you, Vipul. Over to you. So
Thank you so much though, for the kind introduction. Can you confirm my screen is visible
yeah, Vipul,
and
your
audible
screen
also?
is visible. You are also audible.
Okay, thank you so much once again.
Mhm.
So welcome everyone. So today's session is about, first of all, I would like to congratulate FOSSI and IIT Bombay team for organizing such a useful program or for faculty development. I think it's high time, like in India, we need more and more faculties who should be like well trained to pass on the very critical knowledge about semiconductors and especially in design field. And I think there is no better platform other than the open source ecosystem, which has very well established in last 5 6 years. And FOSSI in India is playing a very big and leading role in that to basically percolate that to the maybe tier two, tier three cities and colleges who are maybe not in the thick of schemes or whatever semiconductor development is happening in India right now through various government schemes. But I think open source along with eSIM provides a very good platform if you want to learn and also pass on that knowledge to your students and other people in your organization. So before we start, first let me just give you a brief introduction about what exactly is open source. Because typically what we understand is IC design is a very complex and time intensity intensive and also cost intensive field. So everybody thinks like if you do not have very access to costly EDA tools from big vendors like Cadence, Synopsys, Siemens, so you cannot do chip design and you cannot enter this field. But I think that myth has been broken with the advent of open source ecosystem in world. And I have basically first-hand experience of working in that. I have worked extensively with in industry also with commercial tools, all kind of EDA tools, and now I have experience of open source. So I can vouch, like at least for people who are entering into this field and who do not work with very complex designs or whose requirements are not very state of the art. For them, there is no limit which is posed by open source tools. And I think for them, it is kind of a boon because you are not restricted by all the bells and whistles which are associated with accessing commercial tools and PDKs. So few of these I have mentioned here. One is like commercial EDA is very costly. If you talk about industry, this is the kind of cost which you pay for single license per year under 200K. although I think most of you must be from academia, but still I think it costs significantly from academic point of view also. Also, it is good like government is subsidizing and providing these tools free of cost, but I think not everybody can be served by those two. India is a vast country and we have so many colleges and so many students. I think it's kind of impractical, like commercial tools can be passed on to everybody at cheap cost. And I think open source tools and PDKs fill that gap very well. Then even if you have tools, then Foundry PDKs are a big headache. Foundries, they are not very, like you can say, customer centric. You have to prove your worth to them in order to get access to their PDKs. And even then you have to sign a lot of NDAs and legal requirements. I think it's kind of not practically feasible for a lot of academics and colleges to go through that route. Although in India we have only one foundry, SL Mohali, but still, if you have certain requirements, I think SL Mohali cannot fulfill all those requirements. If you want to have PDK, you have to go to outside foundry, and then they will put a lot of obstacles before you in form of legal requirements to get the access. And then another issue is like if you want to build a very big workforce, like what India wants right now, and the way the world is going in semiconductors, it kind of becomes a limitation if you go through the commercial ecosystem. So there are a lot of obstacles which are kind of restrictive to impart the semiconductor knowledge to the students in colleges or academia. And as I mentioned, the commercial ecosystem is very like pretty close loop. But Open EDA, Open PDK, and IPs, and then there are a lot of low cost shuttle fabrication which are available right now with tiny tape out kind of facilities, which can fabricate your designs in as little as $100 to $200 kind of cost, which was like kind of not thought about in 5-6 years times from now. So all these are the benefits which makes open source IT design ecosystem kind of parallel offering, especially for academia. I think that is a very big benefit, which kind of levels down all the issues which are associated with commercial ecosystem. So if you want to compare, like on the top is a flow, how a commercial ecosystem works. If you want to design and get your design fabricated, you start with commercial EDA tools. You try to get an access, which obviously is under NDA. Even if you do some design and in that PDK, I think you have some restriction on sharing it publicly online. Then you design a proprietary IP, high fabrication cost. If you have to go to some outside foundry, so I think government is subsidizing SCL fabrication, but if you want to do some outside fabrication, it's not possible. You have to pay significant cost, which can come in thousands of dollars. And then at the end of it, you get a fabricated design. But now similar basically facility is available in open source flow. You start with open source EDA, which is free of cost. You pay no cost. You go online, get to GitHub and download the tools, and you can work easily with them on your laptops. Then you have PDKs, open source PDKs, which are available publicly, like Skywater 130 nanometer. Then there are GF, IHP also. So there are 3 PDKs right now available. Using them, you can basically realize your designs. And the IPs which you design, realize using those tools and PDK, they are open source. There is no restriction on you. If you want to share it, you want to publish it, you want to show it, your basically achievement online somewhere, you can easily publish it. There are no restrictions on sharing it. And then one big advantage is, as I mentioned, tiny tape out. The fabrication cost has been very, very basically minimized, because not all academic designs or student design, they from the first days start with complex design. The area requirements are very low. Maybe 100 micrometer by 100 micrometer, you can design a very good op-amp or band gap reference or some that kind of a circuit. So you need not pay a full cost of a complete 3mm by 3mm cross chip, which comes in thousands of dollars. So by like that tiny tape out facility, it has really subsidized the cost. And then at the end of the day, you can get your design fabricated. So the basic takeaway from this slide is you need not be restricted by commercial flow, commercial EDA in order to get your design fabricated and see your idea which has been realized on silicon. So this is just a comparison. I think if anybody of you must have worked on commercial tools. So these are the tools like Virtuoso, Spectre, TVS, Assura, Quanta, similar tools from Synopsys and Siemens. So idea is like whatever tools which you use in your commercial flow, similar kind of tools are available in open source also. And now with eSIM being provided by IIT Bombay through FOSSI, I think it is kind of an homegrown solution which is available to you to realize your front end design. So idea is you're not restricted by tools. Don't think like what tool I will use for what that particular spec. If you want to do schematic, you want to do simulation, layout, everything can be done with open source tools. And you're not dependent on it. Like you need not worry about licensing and installing and all those kind of barriers have been very well taken care of in this flow. So this is a typical analog EDA design flow. I think myself from analog and RF background, so I want to present this to you. So this is the kind of a typical custom design analog flow. You start with schematic capture, then you do simulation, waveform. You want to see AC, DC, transient, then move to layout during physical layout stage, and then DRC, LVS, parasitic extraction, and post layout simulation. So as you can see, all are these typical custom analog design flow at various stages of your design. And there are other tools or software available in open source domain for each of these steps. So there is no way you are limited. If you have an idea, if you want to design an op-amp or whatever circuits, you can start with your idea, convert it into schematic, and then right away take it to the complete flow, and then you can do your tape out. Okay, so now let us come to our main topic of today's talk. This is PDK. So as we know, it is called process design kit. And what is this? Basically, it is kind of a file package. I think most of you must, if you have seen it, it is kind of a big bulky zip folder or a tar ball kind of a folder which you get from a foundry. And inside it, you get a different kind of folders, subfolders, subdirectories, and there are different various kind of files which lie inside it. So what exactly does PDK represent? It is kind of a software format of files which the EDA tools which you have in your flow, which that PDK recognizes, and in that form, the fab passes on its fabrication information inside that PDK to the designer, and it is meant for that specific tool only. So mind you, if you are working with Cadence, then you need a Cadence PDK. If you're working with Synopsys, you want a Synopsys PDK. If you're working with open source tool, then you need an open source compatible PDK. And what is inside those that PDK? There are spice models which are required. Basically, they capture the electrical properties or the characteristics of the devices which are available in that process. If it is a 130 nanometer, 180 nanometer SCL, sky water, GF, whatever. So those whatever are the electrical characteristics of those devices, MOSFETs, NMOS, PMOS, polyresistors, MIMCAP, diodes, all that are captured in form of the spice model. So these are required during the simulation stage of your circuit. Then there are design rules. These are the DRC rules, which are basically required to check whether whatever layout has been done, has it been done in the manufacturable format as per the foundry requirement. They are present. Then devices and pieces. These are required during the schematic stage, schematic entry and simulation and layout for pieces. Then there are technology layer files. Whatever masks are used during the fabrication, they are being represented in form of layers, which are present in the PDK in form of technology layer files. Then LVS for checking whether your schematic layout, whatever has been built, is it electrically similar to whatever schematic. So that information is also available in form of PDK. And then there are standard cells and IO library. So basically, you can say these are kind of infrastructure which a designer requires, apart from getting an access to EDA software tools, and this infrastructure is being compatible to that particular tool set. Then only a designer can proceed ahead with designing a circuit. So as can be seen at the bottom of this slide, if a designer is available, like you have an idea and you have an access to EDA tool, then you need a PDK. Once you have a PDK, then only you can complete your design as per the foundry process. And then once the design is done, then you send it to the foundry, for whatever PDK you have designed it for, and then get your design fabricated. So this is what a PDK does. And it is a very important and integral part of a design flow. If you want to get your design fabricated, if you just want to do experiment or something, then there are generic PDKs are also available. But I think the crux of matter is there is no parallel or alternate to learning chip design by getting your design fabricated. I think it is altogether a different feeling if you are able to design your circuit with a proper foundry PDK and then also get implemented it on silicon using fabrication. I think if a student or whoever is interested in this field, if he get to go through that complete process using actual PDK, I think there is no other better alternate than that. Okay, so this is kind of a graphical representation of what was covered in previous slide. You start with the design specifications, then you do schematic entry. At the schematic entry stage, you need symbols and CDFs and callbacks, which basically that is because if you want to change the width and length of your transistor, and then accordingly the parasitics, internal parasitic capacitances or other properties of a device changing. So all that information is basically coded in these callbacks. Then netlist, once the schematic is done, you want to convert it into a specific simulator netlist. Like if you're using ngSpice or Spectre or XSpice, then every netlister has its own format. So that is also basically included inside a PDK, how to netlist your schematic into specific netlist. And then obviously spice models are required for doing the simulation. Once the front end stage is completed, then you move to back end layout stage, and then you need P-cells. Basically, P-cells are a pre-designed layout of your circuits which are programmable. Basically, if you change the width and length of your device, that characteristics also changes the width and length of your P-cell layout also. So those are available in PDK. Then technology file for layout, all the layer information, etc. That is part of technology file. Then DRC, LBS, parasitic. So this is how a typical flow looks like, and these are all the corresponding files which are included inside a PDK. And one more thing, I think most of the times what I have come across when discussing it with, especially for academic, most of the people don't realize what all things lies inside a PDK, because they get pre-installed tools and PDK integrated into it. So they don't realize like how significant a PDK becomes part of your flow. But this is how I just wanted to give you a feel, like all these parameters or files are available inside a PDK, then only you can do your design. And it's a good habit to also explore a PDK a little bit so that you can understand like how the complete design ecosystem and flow works. So now coming specifically to the Skywater PDK, I think which is the focus of this faculty development program, I want to share a little bit critical information like what exactly lies inside a PDK. So this is a PDK which is provided by a Skywater foundry. It is a US-based foundry, and originally it was a Cypress Semiconductor fab, but then later bought by a Skywater company. And it was initially a 180 nanometer node, which was kind of then with little with minor updates, it was basically adapted to 130 nanometers. So that's why it is called a hybrid technology, because most of the things remain same, but little bit variation in that. And then the critical thing is like I think around 2020 timeframe, this PDK or this process was made open source by this foundry. And I think that was a very big step, because before that, no commercial foundry had open source their PDK. I think it was unimaginable to think like a foundry will open source their PDK. And this basically gave a big boost to the open source community, because now you have a real fabricatable PDK in your hands to work with open source tools. Before that, only some generic PDKs or that kind of stuff was available, which are not very fruitful in learning actual design. Apart from that, this PDK, basically this process, it includes 35 masking steps which are used in fabrication. So these are the mask layers which are used to basically implement your layout into the devices on silicon. Like if you're doing a NMOS, PMOS, there are different kind of steps which are included, like diffusion, well generation, source drain implant, poly, gate upside. So all those steps are what all those layers which are part of your devices, they are implementing using masking step. So overall there are 35 masking steps. And then the critical part for interconnects, because building your transistors and devices on a silicon is one thing, but you want to connect it also. So there are 5 metal layers which are available. In overall, there are 6 conducting layers, but one of them is a local interconnect, which is basically recommended only for doing local interconnections. But other than that, there are 5 metal layers which can be used for making interconnect. And okay, so in the bottom you can see this link. So generally, whenever you talk about PDK, it is a closed source, basically database which you cannot share in public domain if you have signed an NDA. But in this case, every information, all the information about this process and devices are available in public domain through this portal. You can go there and learn about all the whatever lies inside it. So this is a big thing which I was referring to, which the Skywater did some 5-6 years back. And this is how a backend layers, the metallization layers, which I was referring. So as I mentioned, there are overall six conducting layers. Five are metal layers, and the lowermost is the local interconnect layer. So if you start from the bottom, these are your basically devices, doping and diffusion layers, which are used to build your active devices and also the passive devices, well resistor, etc. On top of them, then there is a gate polysilicon, and then this green layer is a local interconnect layer. After that, then there are five metal layers. So basically, these are required if your design becomes more and more dense. Then you have to, and that especially happens in digital designs, because then there are a lot of transistors and there are a lot of interconnect. Then you have to utilize most of these layers in order to make proper connections. But even though if you are doing analog design, then also you have to use these layers, because ultimately your power supply and the ground connections will come from the top, and also all your signals, everything will come from top, and then through vias they get percolated toward the bottom. So this is how the stack structure looks like for this Skywater PDK. And then these are your front-end layers. Front-end layers, I mean, these are the layers which are basically doped or implant inside your wafer in order to realize your devices like NMOS, PMOS, if they are BJTs or some well resistor, etc. And then there are diffusion layers and the tap regions, which are used for substrate connections, which are made using N-well, 2-well, and then local interconnect in order to make connection between local devices on the bottom lower surface of your stack. And then this is a gate oxide, and this is a gate connection. So this is how your front-end stack for this PDK looks like. This is basically a cross section view of that your devices. And then there is also the MEMCAP registers are available in this PDK. So these are called metal insulator metal capacitors, and these are special capacitors which require extra masks in order to realize them. So let me go back to this stack, and if you can see this particular region between metal 3 and metal 4, so there is a basically a dedicated mask used to realize this metal layer, and then between that metal layer and this metal 3, a capacitor is formed, and the connection bottom layer connection is taken from metal 3 and the top layer connection is taken from metal 4 for this MEMCAP. This is the first MEMCAP, and then similarly there is another MEMCAP between metal 4 and metal 5. And these two MEMCAPs can also be connected in parallel. They are basically stacked MEMCAP, it is called, in order to realize the high density. If you have a big capacitor in your design, you can use both these capacitors in order to connect in parallel. And one more important thing about CMOS technology is like the capacitors take a very big area in your designs. So that's why foundries basically they implement different kind of structures or MEMCAPs in order to increase their density, capacitance density, so that within a smaller area they can realize larger capacitance value. So these are the MEMCAP capacitors which are also present in this PDK, and then there are two types of MEMCAPs, this one and the upper one. Yeah, as I mentioned, and one more thing, if you have a MEMCAP in top metal layers, so if the region inside it is empty, you can use this region within your layout in order to realize your design. So it's not like if your design has a vacant area under the MEMCAP region, then that can also be used to put your devices, any transistor, resistor, etc., so that it will become more compact. And then the Skywater also provides this topmost layer. It is called redistribution layer, and this is a copper layer, but this is not implemented by foundry. This is basically implemented by an OSAT. They have to realize this, and then using copper, they basically realize metal balls over the top of exposed pad regions of your die or wafer, and then this helps in order to implement a flip chip kind of a package. The benefit of flip chip is if there are no bond wires, basically a big or a large 1 mm, 2 mm kind of bond wires which are required in order to make connection to the packet, then it reduces the inductance to your die. And then it becomes critical for high frequency kind of applications, specifically when you talk about RF domains where inductance can basically affect the frequency and also gain performance of your design. So in those kind of application, if you want to use basically solder bump kind of bonding scheme, then this range distribution layer can be used. This is also part of this video kit. Okay, so one important thing is whenever this basically applies to any PDK. So whenever you work on a new PDK, it takes some time to get basically understand how the nomenclature of devices and various kind of libraries which are part of that PDK is. So in case of this particular PDK, Skywater 130 nanometer, so this is how basically convention of libraries look like. Skywater underscore vendor. This is basically whichever vendor has developed that particular module, and what is that library, what is the purpose of that library, and what is the type, basically what kind of device or any specific cell that is, and then the final name. So if, for example, if you go inside that predicate, if you search for this particular cell, so in this case, it starts with Sky 130. It means this is from Skywater Foundry and 130 nanometer node. FT means Foundry. So this has been provided by Foundry itself. So no third-party IP vendor has developed that module. So Foundry itself has provided. So in this case, that's why FD is used. If there is some other Foundry, so there might be some other abbreviation available for that particular vendor, or if it has been generated by him. Then SC means these are standard cells. This component is part of standard cells, which are used for basically digital design. And this is a high density. HT means high density. There might be a low power kind of module or something like. And then finally, the name of that cell. This is a NOR gate to input NOR gate. So this is if you want to understand, basically, if you see some conventional name inside your PDK, you understand like what particular this component or module refers to. So this is how you can debug that. And similarly here for a min cap capacitor. Okay, so if now basically transistors are kind of a engine of any technology, because these are the transistor which drives the performance of your designs, what kind of circuits or designs you can realize in that particular technology or new. So in kind of Skywater 130, 1.8 volt, these are standard NMOS and PMOS. These are just for, like, I want to show you, like I have not covered all the devices here, but this is how you basically understand the properties of your MOSFET transistors. This is a standard 1.8 volt NMOS. And these are the ranges. These are the VDS, VGS, and bulk source ranges. These are the limits. I think beyond this, you cannot put the voltages across the junctions of these transistors because they have been characterized for these particular limits only. If you apply voltages which are basically violating these ranges, I think the foundry takes no accountability of that, or they do not guarantee the normal performance. Your devices, your junctions can break down and your devices might stop working. So that's why these limits are provided. And then threshold voltage, and these are some parameters which help you to understand what kind of basically current performance with respect to width and length it can provide. So when you start your design, you obviously start with front-end design, schematic design. So this is how the symbol of NMOS looks like inside for an Xclean tool. And this is how the naming of this cell is inside this PDK, as I mentioned in my last slide. And similarly, this is for PMOS. And these are the cross-sectional views of these NMOS and PMOS transistors, how basically are dopings and how the different regions are implemented in order to realize these particular transistors. These are for standard VT transistors, and similarly, there are also high VT and low VT transistors available in this PDK. And high VT transistors are used if you want to do a low power kind of a design, and low VT transistors are used if you want to do a like kind of a high speed design. So basically, standard VT is kind of a trade-off, a balance between high speed and low power kind of requirement. So basically, it means based on what exactly your design requirements are, you have to choose. Basically, this is a kind of call which a designer has to take before starting his design based on the specifications. What kind of transistor I have to choose, whether standard VT transistor will work or I need to use a high VT or low VT transistors. Then this basically this PDK also has accumulation mode MOS character. This is basically a variable capacitor. The MEM cap, which we saw earlier, they were a fixed capacitors, like their area is fixed. So they provide a fixed capacitor, but this is a MOS-based capacitor. So by changing the biasing of your MOS, by keeping it into either saturation or linear region, you can change the capacitive properties of your transistor, and then that basic property is used as a variable capacitor. So this kind of device is basically required when you have to do some kind of a tuning of your design, like in oscillators specifically, the voltage control oscillator, where you want to vary the frequency of your circuit or oscillator with some control voltage. So this is where this kind of a device is used basically. And these are the symbols when you go inside your PDK and try to look for that device. This is how this will look like. And these are the model names and the servers inside the PDK. Then there are bipolar transistors also available, BJTs, but mind you, these are not kind of optimized devices which are basically developed by a foundry. These are kind of parasitic BJTs which are realized based on how the MOSFETs are being designed in process. Basically, because whichever design devices are part of the PDK foundry, they are well characterized and well designed by the device engineers inside fab. But in case of bipolar transistor, so, and obviously if there is a special kind of a device like MIMCAP is a special kind of a device, you have to add extra masking layers in order to realize that transistor. So that is basically, you do not want to waste that masking just by keeping a kind of a parasitic design in your process. So this that is well optimized and well characterized, and all the rules and everything is well defined for them. But this is same is not the case for bipolar. Bipolar transistor, these are called kind of a parasitic bipolar transistors, and they are what which get automatically realized during the process of is basically optimizing and designing a MOSFET for your process. So basically, the idea is it's not advisable to use these bipolar transistors for some kind of high accuracy or high precision design. They can be used in if you want to do some kind of a band gap reference design where you want to basically extract the junction diode, PN junction diode properties in your design. So there these can be used, but please do not use them if you want to do some kind of high gain op amp or a very low noise op amp and use try to implement it these BJTs in the input stage of your op amp. So that is not recommended. So that's why at the bottom you can see it is written these devices are free. They are not optimized properly. And besides these, there are a lot of generic resistors which are available inside this PDK and process. And by generic resistors, I again mean similar to BJT. These are not the devices which are basically optimized for their performance. These are whatever has been realized during the fabrication process when you are performing when you are basically diffusing an implant NFP on your wafer for realizing NMOS or PMOS, or you are doing some kind of implant. These devices are basically realized from those layer properties. So these are diffusion resistors N plus P plus when you are using these for source strain kind of development, and then P-well, then the P-well resistors can be realized from your P-well region. Then similarly, whenever metal layers, the primary task for metal layers is to make interconnects between different nodes in your layout. So whatever resistance is basically realized during that definition or designing of those metal layers, that has been implemented as a metal resistor in different. So idea is like these are available in your PDK, but again, if your design is like high precision based, so these are not recommended there because again they will have not very good control over their properties. They might have some kind of a voltage variation or temperature variation. So for high precision analog design, there are different set of resistors which are recommended, which I will cover in next slide. So yeah, these are the resistors. These are polysilicon resistors, which are basically, it is a doped polysilicon. Polysilicon is same way which is used to relay the gate of your MOSFET. And by changing the doping of that polysilicon layer, high precision resistance can be realized. And depending on how small or how high the doping is done, the resistivity of these resistors are defined. And these are very well controlled. Like you do not, there is obviously there is still some variation with voltage or temperature, but it's not as high as for the previous set of resistors, which are generic resistors. So these are the resistors which are recommended if you want to use for some high precision circuits. And again, inside this PDK, there are different types of polysilicon resistors which are available based on what kind of width is predefined in the P cells. So there is a 0.35 micron width poly resistor, 0.69, 1.41, 2.85, 5.73. So these are the different P cells which are already available in this PDK. And designer only has to change the length while realizing a specific value. For example, if you want to realize a 10 kilo ohm resistor, so based on the sheet resistivity and the width which is available, you can find out what is the width and the length of that resistor. So that's how you use polysilicon resistor for your design. Okay, so this is again the MEM cap which we discussed previously. So this is how a MEM cap is realized. The first MEM cap is realized between metal 3 and metal 4. And the connections are taken like this. For this MEM cap, the top layer, the connection is taken from metal 5, and the bottom metal 3 connection is again taken from metal connected by connecting metal 4 and metal 5 through via. So these are the two nodes which will be available when you are using this MEM cap. And if you are using a top MEM cap device, then the two terminals which will be available for this MEM cap to metal 5, both the terminals will be available to metal pipes, like in this case, as this drawing shows. And this is what will be the cell name if you go inside your PDK and try to search. And this will be the model name inside your SPICE model for this name caps. So there another type of capacitor which is available inside this PDK. This is called vertical plate capacitor. And this basically is realized using the metallization layers, which are basically already available in your process for some other purpose, that is for making interconnect. So basically, this exploits the property of basically laying out these metal layers very tightly, because the smaller the difference between the metal layers will be, like the smaller the dielectric layer between the two metal sheets will be, the higher the capacitance you can realize. And by laying out the layout structure of this capacity using these metal layers like this, by making it very tightly spaced, you can try to basically realize some kind of capacitance, a good quality capacitance with this kind of configuration. So again, if you have an area, or if you do not have any area penalty, or you want to save area for your design, and you need a high precision, then it's preferred to use a MEM cap. Vertical plate capacitors are only used when you do not require a very high precision capacitance, or you do not want control over the variability of capacitance value, and also you want to save the cost of your fabrication, because in MEM cap these extra masks will be used. As I mentioned, there are 35 masks. So the two separate masks will be used for these two capacitors. So every mask basically add to the fabrication cost of your circuit. Whereas in vertical plate capacitor, there is no such masking requirements. So in this case, basically for this you do not need to pay anything extra. But for using MEMDAP, you have to pay extra for the masking device. Okay, so I think these whatever things which covered for right now for PDK, these are called primitive components. Basically, these are the devices or components which are primitive, basically which process is based on, and whatever files or components you use or the libraries you use for digital design, these are derived using the properties of these primitive components. Like in standard cells, there are different kind of standard cells, right from starting from inverters to complex flip-flops and registers, and then gates, different kind. All those cells are being realized from these basic devices which I have covered in my previous slide, and mostly using only MOSFETs. Because for standard cells, we do not use any kind of passive devices, resistors, capacitors, etc. So basically, these are again characterized in form of libraries inside a PDK. And then there are different kind of timing models which are available, and then IO libraries, PADs, which are basically common for both analog and digital design. And then in case of digital design, you use a RTL synthesis and placement and route kind of a flow. So for digital design, these are the critical components, standard cells and timing models, which are exclusively required for digital design flow. And they are also provided as part of a PDK. But generally, I think there is a kind of a misunderstanding. I think what these things which are referred to digital PDK, they are not exactly PDK, they are basically libraries. PDK is whatever is basically kind of a primitive components, which are actual fundamental devices, which are basically designed inside a fabrication process. These are not actually fundamental devices in that form. These are basically derivation from the fundamental devices of a process, which are then converted into form of a standard cells, and then they are further used in order to realize some kind of a digital circuit. So yes. And another thing is most of the analog design flow steps, these are manual, and all the files which I have mentioned before, they are used during different steps which are followed for analog flow, schematic, simulation, layout, VRC, etc. Whereas in digital flow, most of the things are automated. I think the tools handle most bulk of the load. With there is some feedback which is provided by the design. But then more or less, not more or less, but basically they use a similar kind of files or PDK in the background. Okay, so specifically talking about open source, one thing is this is basically used in Linux. In fact, most of the commercial tools, they are also used in Linux. So there is no role of Windows as far as IC design is concerned. So I think you have to have some know-how or background, basic know-how about how to use Linux, and then typical setup required. You want to use using the virtual box or something. And I think one thing is for sure, this can be used within your simple laptop. You need not have a complex or very high-end servers or some kind of a data center built in your colleges or in your universities, wherever you are working, in order to use these tools and use this environment. So that is, I think, one of the biggest advantage of open source ecosystem. Like this gives you a basic freedom. And another thing is, when you work on these tools and you have installed in your laptop, you can go anywhere and start working on it. One thing which I have found in academia is like students are bounded by their labs in your colleges, and it's open for specific time period in their time, and also there are limited number of licenses and seats. So there are no such limitations with open source. Anybody having a laptop can simply install it and start working on it using whatever design you want to play. Okay, so I think we just discussed about Skywater till now, but I again want to emphasize like this open source movement is growing big, and these are some of the timelines. It basically started in 2018 when OpenCode was launched, and it was a DARPA funded project. So even DARPA kind of realized the potential and utility of open source. And the big movement came, as I discussed earlier, also in 2020 when Skywater open sourced their PDK in association with Google, and they also funded some of the earlier free shuttles. Then OpenLane was established. OpenLane basically gives you a liberty, like even if you do not understand the nitty-gritty of different design steps and design flows, especially in digital, and you just understand Verilog and you know how to code your circuit, and you just come with your Verilog and you have a pre basically designed fully integrated RTL to GDS flow in form of open loop. You give your Verilog, and at the end you get a GDS, which is basically ready to for fabrication. Then in 21 to 23 timeframe, two more foundries open source their PDK. That is Global Foundries 180 nanometer and IHP Germany 130 nanometer. And IHP Germany is special because it is a very high-end PDK. Silicon germanium, high frequency RFIC design can be done, and it has an FTR of more than 200 gigahertz. So it basically opens up one more avenue for IC designers who are interested in doing RFIC designs. And then I think there has been pretty lot of development which are happening in last 2 years. And I think recently, just last month, I think, or maybe this month only, SL Mohali, they have also announced like they have open source their, although it is an old node, but I think then also it is a big step, at least in Indian ecosystem. They have open source their 1.2 micron CMOS PDK. I think it will be very beneficial, at least for Indian open source community. So yeah, just few concluding slides. I want to emphasize like PDK is kind of a bridge between a designer and foundry. People generally, at least who are in their early careers in chip designing, they do not realize the importance of PDK, but it is very, very important because it all depends on the integrity or quality of your PDK. That whatever things you are seeing during your design flow in EDA tools, whether whatever simulation you are doing, layout you are doing, whether those results will be realized on silicon. If your PDK is high quality, good, and your models are good, and all the verification checks are properly implemented inside PDK, then you are assured that things you are seeing in your simulation environment or in your designing flow, that will be implemented on silicon, and you have a good chance of success with your silicon. But if it is not, or if something is missing in that PDK, or that PDK is not a mature PDK, let us say a foundry is working for the first time and they have developed given just a initial version, test version of their PDK, then there are chances like things might not match. But generally, a PDK is a very important part. It is a bridge between designer and foundry. And these are the things I think which we already discussed, what all lies inside PDK. And okay, one more thing, it's good habit. Like before starting any design, just go inside the PDK folder and try to explore things like what all things are lying at which location and what those represent. Especially for analog design, where a lot of times a designer, when things start failing or some things which are not mapping as per your expectation, then a designer has to go inside a PDK folder and then do some kind of a cross checking. This helps to basically debug your issues. So it is a good habit. And in the end, just to give you an overview, this is how a complete analog design flow looks like. Specs to post layout simulation. And once and at each of these steps, which are you go through your design flow, the PDK plays an important part. A specific module or file inside a PDK is basically integrated into your tool in order to implement that step. And once the post layout simulation is done, you're happy with your design, like whatever done is basically is okay. Then comes the part of tape out, which is basically nothing but just generating a GDS2 format of your layout and then passing it on to Foundry, which then converts it into a mask, and then it sends it to a Foundry for fabrication. So in conclusion, just want to highlight specs are important. Like whatever designs you are doing, you have to basically and align with your specification first. Do not try to keep on changing them. And whenever you're designing with whatever tools you are doing or whichever PDK, iteration is normal, especially in the analog design. You do not expect everything to fall in place in first go. Don't expect like if you have done a hand calculation for a 80 dB gain open, and in first simulation you will realize that gain. It doesn't happen like that. So you have to iterate, you have to go back and check your operating points or whatever analysis you have done, and then make a conclusion like what things needs to be changed. So that is pretty normal part of your design flow. And at the last, PDK is a binding. So whatever things you do, it all basically maps to your PDK. And one more thing, I think sometimes I have heard like people try to also play with PDK, like they want to change something or please don't do that thing. Whatever things in whatever form PDK is being provided to you as a designer, just use it. Do not try to go inside it and change something as per your convenience or whatever you have thought about it. So that is not basically advice, because if you make even a small change, you don't know exactly and what role it may play on your design for that particular step. So please avoid that. I think that's all from my side.
Yeah, hello. Thanks, Vipul, for the insightful talk. And we came to know about a lot of things, including the history of Sky 130, how it came into the picture, and how things are working inside the PDK. Many of us only know the full form of PDK as Process Design Kit, but what's inside that, many of us don't know, and it's a matter of curiosity all the time that what's going on inside. But you have explained it in a very easy format to for the newbies to get to know about the things. So anyone wants to ask anything?
Yeah, please, any query, I'm happy to answer.
So it's a privilege to hear the Vipul. He has a lot of experience in fabricating. He has worked in in the SCL Mohali. So yeah.
So I'm sharing my email ID. If anybody has any follow-up, maybe they can pose any query later also.
Okay, sure. But anyone wants to do it right away?
Yeah, that's also fine.
Yeah, someone is asking from CSIR Siri that once we make analog, let's say ADC, can we import that in digital in this flow?
So basically, if you are talking about ADC, ADC in itself is not a pure analog circuit. It's a mixed signal circuit. It includes both analog and digital components. So both those components have to be designed separately in analog and digital flow, and then they have to be integrated during simulation for validation in mixed signal simulation flow. And similarly in layout, you have to basically you have different macros, analog macro and digital macro, and you have to combine. So if you want to import a pre-designed IP in a digital flow, I think that is possible, but then you won't get a transistor level design or IP of your ADC in your digital flow. You will kind of get a module which basically what I should it will be kind of a model of ADC which you can import in your digital design and then try to implement your circuit over there. So, but that is more a part of a mixed signal flow. Can we say Sky 130 PDK is fabrication ready? Can you? Yeah, definitely. I think that's the whole point of my talk today.
Yeah,
Sky, in fact, uh, I think Sumanto also knows about it. Especially, it is very popular outside India. People are fabricating thousands of designs,
yeah,
and there are a lot of shuttles which are taking place from Sky 130 GF and also IHP. And the cost of that fabrication has also been reduced significantly. Like people pay only $150 to $200 to get their design fabricated. So it's very much fabricatable. And now people are also trying to do commercial design on this.
and YouTube.
YouTube channel,
Yeah.
I think there are a lot of stuff available on YouTube. Please try to search and you will find something relevant for your requirements.
So there are
If I do a
videos. There are videos by Matt Finn and people like that who are the people working in Sky 130. There's also Open Silicon Slack channel that you can join and get to know what's going on. Yeah, people
So
very
once somebody asks, if I do a design using Cadence, can I use Taiwan water prediction in later stages, or should I use? I think it's possible to do, but I think it's not advisable at all because it complicates things a lot. If you want to use Cadence, please stick to Cadence. If you want to start with open source, then start with open source tools only. Don't try to mix the different design steps in different tools. Is it possible to perform PVT and Monte Carlo analysis? Yes, I think it is possible.
yeah. And
I,
this
I
pass
have
work.
done Yeah, I have done PVT analysis, but not use Monte Carlo. But I think I have seen people using Monte Carlo also. This
It's
Sky
possible.
132.
Mhm.
Can we translate our design from Sky 132 synopsis PDKs? I'm not sure it can be done. At least not for 130 to 32 nanometer. I think I'm not sure about that. And I think you have to explore further on this.
So the since Sky 130 is in 130 nanometer, you can port it to some other PDK in that range, 180 or something. But 32, I don't know.
But then also you cannot put files exactly. You have
Yeah,
to,
yeah,
you can put your design, then you have to tune that design in that particular
that
PDK.
particular, yeah.
So what are the common mistakes designers make during the schematic to layout process? How can we verify that a layout is manufactured? Okay, that's a very good question for beginner at least. So once you have moved to layout stage, I hope you are convinced with your front end schematic design. You are okay, whatever specification you see. Then you do a layout. Then first step in layout is you have to check LVS, layout versus schematic. You have to ensure whatever layout you are doing, you are building manually, is it complying to your schematic? Whether all the devices which are placed in your layout, they are with proper W by L, or with, whether they are using proper interconnect. So that check is being done with LVS, layout versus schematic. Once that is done, you do DRC, design rule check. The purpose of DRC, because Foundry has its own requirements and limitation by how you can place different devices and layers in your layout. So that check is done using DRC. So as far as Foundry is concerned, they only require DRC clear. They do not they don't have anything to do with whether you have checked LVS or not. But as a designer, you have to do LVS and layout DRC checks. Once that is done, you're assured like your design is manufacturable and your circuit layout is electrically equivalent to your schematic. But then there is another check which is optional, but it is, I think, must be done more analog. That is parasitic extraction post layout, because after layout some parasitics get introduced due to the use of interconnect layers. So you have to basically account for their performance, their effect of their on circuit performance, because due to those parasitics, your delays might change, your gain might reduce. So all those things you have to check with post layout extraction. So these checks, if you do DRC, LBS, and parasitic extraction, and all your design passes through these checks, then I think it's well to go for manufacturing. Is it possible to install Windows OS? So you cannot install these tools on Windows OS, but inside Windows OS you can either use Docker containers which are available, or you can use VirtualBox. Inside VirtualBox you can install Ubuntu, and then inside Ubuntu you have to install these tools. So these tools cannot directly work on Windows. They need a base OS of Linux at least to work.
Just step to import the SCH of ngSpice into .v. You mean the netlist to .v? Yeah. So is there a netlist to .v converter?
I'm not sure about this. Maybe I think because I'm not well versed with digital flow. But why do you want to convert .csv? If you can tell me your application, then maybe I can suggest you some other way. But I'm not sure about this thing. Maybe you can drop a mail to me and we can discuss that.
Yeah, there were some work done in this domain. I will search and send you some links maybe. But yeah, completely it's not possible to convert uh, netlist to .v.
I'm currently working on LNA for drone detection radar in 180 nanometer. I have very limited time for to work with cadence virtue. So later can I use this at any time? Okay, so Chavli, I do not know whether you are a student or academic, but I think this is a specific kind of use case where open source can help, because LNAs, I think you are working in RF domain. So now you have an IHP PDK, which can very well realize LNAs up to 100 of gigahertz. If you are talking about 180 nanometer, I assume you are talking about SCL. But in SCL 180 nanometer is not RF compatible, so I don't think even if tools can work, I think it's not advisable to do LNA high frequency LNA design in that 180 nanometer. So alternate way is use IHP 130 nanometer using open source tools. You can do RF analysis there, and those tools are free of cost, and you can easily install in your laptop and they'll lay with you. Even if you leave your college or you go somewhere, those tools remain with you. You can anytime keep on working on those tools and PDKs in your design. And if in future you want to get it fabricated, I think there are shuttles available with HP where you can basically implement your design.
Yeah, anyone else has any other query? G2N, GT2N from Georgia Tech is also addition as open source.
Not aware of it.
Not aware of this. Obviously, there are various things going on.
So it will be surprised if 2 nanometer node is open source. So can we conclude, Sumant?
Yeah. Yeah, so if any more doubts, just feel free to mail us. People has already shared the mail ID. You can even keep me in copied to have the talk ongoing. And yeah, so thank you, Vipul, for joining. And it was wonderful interacting with you. Thank you for giving your time. So now Miss Shantipriya will be presenting on a hands-on session. We'll taking a hands-on session on how to design a circuit using Sky 130 in eSIM. So thank you, Vipul. Hope to see you
Thank
again.
you.
Yeah.
Have a good day.
Bye bye.
Yeah. Hello all. Good afternoon. Hope my audio is okay.
Yeah.
Yes. I'm so glad that still you people are enthusiastic up to this session. And sorry for the morning that my system has stopped suddenly. So we can continue in this session. Okay, let me share my screen. Yeah. In the previous sessions, we simulated circuits using generic electronic components, right? Those simulations are excellent for understanding circuit behavior, but they don't represent a real fabrication process. Actually, in VLSI design, we need technology-specific device models. That's where this process design kit or PDK becomes essential. So today we will use Sky 130 PDK integrated with eSIM instead of ideal MOSFETs or other components. We will use transistor modules provided by the Sky 130 technology inside the eSIM. So uh, I wanna discuss why Sky 130 PDK in eSIM. So it refers to the Sky 130 nanometer CMOS technology. The number 130 indicates the technology node, which historically refers to the approximate minimum feature size. I repeat, it's a minimum feature size of the PDK. It is an open source PDK widely used in education and research, as we discussed before, and it has many modules like transistors, spice modules, layout rules, and many are there. Those will help us simulations more representative for real silicon. So uh, let's see what are the libraries that are involved in Sky 130 PDK. So let's create a project. Let's name it as CMOS inverter and create schematic editor. Click on S, load the components list, and it will take some time. And okay, fine. Yeah, it was loaded. And once you type here Sky 130, and you can see all the libraries which are integrated into the eSIM from Sky 130 PDK. Before going into hands-on, I wanna show you the PPT so that you people will get idea what we are going to design and all. Yeah, once we went into the eSIM uh, schematic editor, you have to type Sky 130 mode. If you keep this module inside the schematic editor, that will enable all the schematic works inside the Sky 130 mode. So first thing you have to do, you have to include this module while creating your schematic design. So once you included that, go for the basic design, and today we are going to design basic CMOS inverter. And as you people know, a CMOS inverter requires one PMOS and one NMOS. PMOS provides a path for the supply when the input is low, while the NMOS provides a path to ground when the input is high. As you well known of all these, and after including these components, you have to give input, output, and wherever the plot you want, and VDD. And the output is at drain connection. As you can see the schematic, this thing we are going to design. If you want, you can take screenshot of this schematic so that you people will get familiar while we are going on hands-on. So the output is at the common drain connection, and the input controls both transistors simultaneously. And as you can see, this is the source. As CMOS circuit requires a power supply, and the PMOS connects to the VDD, and the NMOS connects to the ground. And without these supply connections, the circuit can't produce valid logic levels, as you well know about this. And after designing this schematic, and make sure you involve this module inside the schematic editor and save the file. And as you know, you have to annotate the schematic. Then after, you have to create the netlist and go back to the main GUI of eSIM. There you can see the timing analysis section, and there you can enter the start time, step time, stop time as per your requirements. Once you're done with this, you have to navigate to the tab source details. As we saw the schematic that we gave source. For VDD, you can give direct source, direct values, and another pulse we give, so we are giving all the rise time, fall time for that pulse. um, here the pulse value is 1.8. As why 1.8 means, at the standard value of Sky 130 PDK is generally the 1.8 voltage, and there are existed some high voltages also, but for now we are using this. And the rise time, the delay, as you know, the rise time, it determines how quickly the signal transactions from low to high. In real hardware, signals don't change instantaneously, but we can take zero point 0.1 nano. And then after, you have to navigate to the tab device modeling, as we are specially including Sky 130 here. All these options are enabled to us. Once you click on it, you can see this kind of GUI.
and you have to enter the path of that library. But if you have that library specially in your system, then you can add that path. You can here we have that option to add it as a default, because it's already integrated into our tool. So if you once you click on this add default, the path will directly comes into that space. And as we are going to use two MOSFETs, you have to give width and length of that MOSFETs. Once you're done with this, you have to click on convert, so that the KiCad to ngSpice will convert successfully. And after that, we are going to complete the schematic and everything. And um, as you can see, the simulations will be look like this. See, it's a input and this is a output, and this is the, as you can notice, whenever the input transition is high, let's say at the time of 1 to 2 milliseconds, the input is low. As you can see, at 1 to 2 milliseconds, the input is high, as this is the exact behavior of input inverter, right? When the input is low, the PMOS becomes on, NMOS becomes off, the output will be high. And input is high, the PMOS becomes off, NMOS will be on, and output becomes low. So yeah, this is for the demo, and now we can go for hands-on session. And once you create the project, as I said to you, uh, I'm hoping that you can able to create that project. Once you're done with creating the project, go for schematic option, click on it. Yeah, I already opened, so uh, sorry. Yeah, once you open the schematic, click on the components list. Once it was loaded, it was you have to include Sky 130 module, so that to keep your complete design in Sky 130 mode. If you have any questions on this CSV file, okay, let's continue. Yeah, once you kept this module, let's go for designing. Click on A. You have to include the Sky 130 components only. And yeah, this is NFET. Let's keep it here. And for PFET, yeah, this is the PFET library which are going to use. So let's keep it here. Let me zoom it so that you people also can.
Just wanted to say one thing. Please ensure that you take the 4-terminal device as Santi has taken. Don't take the 3-terminal ones.
Okay.
Substrate. Yeah.
It's fine, right? Yeah, these are 4 terminals. Fine.
Yeah. Please continue.
Yeah, I hope it's good now. Yeah, and we need a pulse. Let's keep it here, and we need DC source as a VDD. We can keep it here, and a plot we want for output, and yeah, we can keep it here at the 2 drains connection, and start with wiring. And we will check the output here. Yeah, we need a ground also. Yeah, and these both were connected. So that let's give VDD to PMOS. Yeah, I think yeah, and we need a ground for VDD. Yes. Yeah, I think wiring is fine. Let's keep a plot here for input plot waveform. Okay, keep it here. And for naming, we can label it. Let's label input. And clicking R for rotating the labels. And the label option is available in the right toolbar. You can keep here also an output label. So we can keep it here. Yes, I think everything is fine. Okay. Yeah, now save the file using Control plus S, and then after you can annotate. The annotate option is available under tools and annotate schematic. Annotate. Yeah, once it is done, close the annotate tab. Click on file. There is an option export. Under the export, you have netlist option to create the netlist. Navigate to Spice tab. Click on checkbox and export netlist. That will ask you to save that file. Save the file. Once everything was done, go back to eSim main GUI and click on KiCad to ngSpice converter. And now you have to give timing analysis as 0, let's say 0.1 milliseconds, and this has 10, and yeah, source details as let's see this. As I said, the pulse value should be 1.8 as it is standard value, and 0.1 nano for delay, 0.1, and again let's take pulse as 1, and this is 2 as pulse period is, and the value is 1.8. And we have to navigate to the tab device modeling, and you have to make sure of this option should be done. Enter the path. If you have that library in your system, you can add it here, otherwise you can add it default. it directly comes to your space. And the corner as our N MOSFET with, let's say, width is equal to 1 and length equal to um, 2. Again the same values. Yeah, once it's done, you have to click on option convert. It will show you it was done successfully. Click on OK. And now click on the option simulation in this spice plots. Yes, it will take some time for waveform display. And I also encourage you people to try more examples on this so that you will get idea how to use the PDK inside the eSIM. Just wait for 2 more minutes, it will show you the output. Yeah, as expected, this is the input and this is our output. Yeah, and I think let me see the comments. Okay, if anyone stuck at the simulation part, kindly uh, share the issue so that we can solve in your hands-on session. Afternoon session video that was already shared. And I think there are no doubts on this hands-on, right? Yeah, Raki, that will be shared soon. Wait for some more time. Okay.
Yeah, thank you so much, Shanti, for this session. So before moving further, um, let me talk about one query that was raised yesterday. So let me check the time. It's around 3:43 for now. So do anyone needs a tea break for like 5 or 10 minutes, or shall we go with the yesterday thing? Anyone needed any break for 5 minutes? If not, then we will just continue with the one example of diode where we will be talking about IV characteristics. That is just to get to know that how to use AC. Okay, we'll continue. Thank you so much. Okay, let me share my screen. Yes. Yeah, we will continue so that we can conclude it early. As long as in the today's session we started at 10:30 with from circuit equation to simulation and introduction to modified nodal analysis by Professor Rakesh Sinha that we did. After that, we done with one hands-on on the nodal analysis at 12 to 1. And now in the afternoon session, as we done with the talk on from schematic to silicon, exploring Skywater 130 PDK with eSIM by Vipul Sharma, founder of Navy Labs. And now subsequently we also done with the hands-on for on Skywater, uh, done by Ms. Shanti. So now I will talk about the analysis, the AC, DC and transient that we yesterday didn't complete due to a time constraint. So let me just share my screen. Okay. So as long as my screen is visible, I'm audible. I hope so.
Yeah, it's visible and audible.
Yeah. So we will quickly continue with our leftover things and then we may continue. Right. So as of now, I have my eSIM ready on my PC. So as everyone know, like what we did before for this particular example of half-wave, we done with the transient analysis. So now I will take on AC and DC, then show you uh, how differently we can do different analysis. Okay. Whenever we do transient analysis, by default, it take the operations as voltage versus time graph we got, or current versus time graph also you will get. So let me show you how exactly it's different. As you can see, I will talk about plots first. Let me take different plot in the simulation loaded. It takes some time to load. Now it is loaded. So let's talk about some plots. So this is the plot V1, which is used to plot the node voltage. Parallelly, we have plot I2 to plot the current. So what we will do here, you can see we have added plot V1 with the global label so that it get a output voltage. So let me just quickly simulate it. So you can see the plots are from voltage and time. But now I want to do a current versus voltage, like a IV characteristics. So let me give an example that is there in everyone's laptop. So for that, you need to click on the open project here. Then you need to locate to the FOSSI folder at your local disk C. Whenever you install eSIM, it gets stored in this folder. In this folder, there is a eSIM folder and then examples. So for now, what we have different examples. So to get to know about the DC thing, we will take a diode characteristics. So you can see here, there is one diode characteristics example. And if I go little down, then there is one series resonance. Just you need to double click on it and just select folder. In case you have a rescue backup, you need to delete it and just select the folder. For now, I have already added those projects into my eSIM, so I won't add it again. So let's talk about the diode characteristics. Theoretically, Professor Indrajit sir already spoke about everything. So now we'll see how in simulation it shows. So here just one basic diode as I kept, and which is followed by the DC voltage. And now to capture the current, I added the plot I2. So just by adding it, we already know whenever we design the whatever thing in the canvas, we do two important things. One is annotation, multiple ways to annotate. One is this option, this icon directly annotate. Then there is a tool, and then also you can annotate from here. Once you get it annotated, or you buy by your own also, you can double click on uh, any of the symbol and you can annotate by yourself. And then you will click on file, export and netlist. and we'll take a spice netlist. For now, everything is pre-compiled. The pre-compiled version is already added with the eSim library in your PC as well. So I will skip it and minimize. So when I click on KiCad to ngSpice, now there are three analyses: AC, DC, and transient. For the half-wave rectifier, what we did, we took a transient analysis, we performed that, and we got a waveforms. Now, what I am doing, I am taking a DC, where there are only one source that you can see here, and within this one source, what I will do, the start, increment, stop time are very minimal to just see whether it is working fine. For the other tab, source details, it is like 1 volt, and the device model that I added here is a normal die. One thing that yesterday was like pointed out, that can we model our own diode? Then answer is yes. To do that, this fourth option, model later, you need to click, and I will explain it, but just let complete the simulation for now. Once we added the library, we need to click add, and then you can see there is a diode folder. Within a diode folder, we have multiple diodes. But if we want to have your own diode for the particular application, that we can do, that I will just talk after this. As we took the d.lib as a normal diode, a general diode I could say, and once we converted it from here, we will simulate. As it is a pre-compiled model, I will just simulate, and I will click yes for the ngSpice plots. And this is the current versus voltage graph for the diode to see the voltage sweep. So if you want to use the Python plots, it is advisable to use the branches instead of nodes. So this VU1 branch will be same as the ngSpice plot is showcasing us. And if you want to look at it in a negative way, then you can take a first branch and plot it. So you can see, even if you want to compare, you can do. Now the point is, we talk about transient, we also talk about DC. Let's take an example of DC. Within that same folder in the FOSSEE, eSim, an example, we have multiple example. The one that I took here is the series resonance. I will just double click on it, and I will show you what the schematic content. So this is also a small schematic which contains one AC and one like a RLC circuit. So what I am doing, I will just perform a same operation on here as well. To do so, I will click on KiCad to ngSpice. This time, as this example is already selected as a EC analysis, just because this is the pre-compiled example that we provided. So we'll keep the values as it is, and to see the output. So we can see the source detail, we could change the ngSpice model. I want to show you an example where we could add a ngSpice model that I will show. Device model everyone knows, but in this example there is no model to add, so it is empty. Sub-circuit, microcontroller, done, and I will simulate. So yeah, this time you can see this is with the frequency. So yeah, so this is like voltage versus frequency graph. One we did, that is current versus voltage IV, and one we that initially did was voltage versus time. So and one more thing that I want to highlight is, as long as everyone has eSIM installed in their workspace, I want everyone, dear faculty member, dear researcher, dear electronics people, dear students, to look into the different examples where you can see different analysis. Actually, what happens whenever, in case any faculty is watching this, if they are teaching this thing in their class, and then if student come and ask, sir, we are finding difficulty to assign the parameters. uh, being 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 you as a faculty, it is very easy for you to um, understand which parameters to be added, but in perspective of student, they sometimes feel difficult to add the initial parameters, maybe if they are in very early phase of their btech. So for them also, this example library is well, like it is very nice, so that they can directly take a reference. They can follow the pre-compiled version of the project, and they can find the parameters values which are needed to simulate the basic examples. And yeah, this is a very good case in this scenario. Now I will talk about that model creation, what that model creation means and how you can have it. Here, as I showed for the device modeling, we took a diode just because the canvas has a diode, and we want to m- make sure which diode is being used. So for that, as I click yes and open diode folder, there are multiple ones. Now my query is that I want a new diode with my property, like whatever that I want to be get simulated. So how I will do it? So this is the fourth option, model editor. I will click here and I will click on new. Once I click new, I can name it anything. For now, I will just keeping it as a test to show you. Once I created a project in the same just that library, it will lead test.lib file. And now we have option of different models: diode, BJT, MOS, JFET, IGBT, and magnetic core. Once we click on any of the, it will give us a chart to change the values. So either these values, like for default and generalized values are being set. Other than this, if you want to take, then you can take a reference from any datasheet of a particular manufacturer, or in terms of research, you can change the values and check whatever the simulation is now behaving. So for MOSFET, again there are different things. So in this way, once we're done, we will just click on add. We need to add all parameters, then that file will be saved. And this file is nothing but the same file that we are adding here. So this time we will add our new file, whichever it is, like a test.lib. And in this way, we will again do the same simulation, and we can see whether model is able to create. So as of now, at the very beginning, we install eSIM. On second and third lecture, we've seen 1, 2, 3 options of the eSIM. Fourth, I just talked about, and this sixth one, in the evening, yesterday's evening session, Shanti talked about this option called Make a Chip and NGVD. Now the only this option remains. NGSDL and Maker chip work similar, but the sub-circuit feature is to create a sub-circuit of the particular component. So let me show you that. So let's take any schematic. Mm, I have this schematic. So what I will do, I will go at the any end. I will press A, and I will show you one library. So So you can see this library I'm talking about is eSIM underscore subcircuit. So this subcircuit library is there in eSIM, and we are actively hiring interns to add many more component in the same ICs. We call it as IC, integrated circuits, and sometimes blocks. So whatever screen task we float to get in get the students enrolled in the FOSSI internship, and we majorly give them a chance to work on this part with, and at the end their particular examples, their ICs got integrated with the eSIM, and this is a very nice way to build a wider library in the open source. So you can see this is the different IC modules that we can directly take and use. So these are the symbols. So how this feature is related to it, I will show. Now I take any random example. any of the, I will just click OK. I will put it here. As long as I know it is a CD 4000 underscore nor, what I will do, I will minimize this. I will come to the main eSIM GUI. This fifth option of sub-circuit, once I click, this window is appear. Now I will just click on edit to see what is inside that CD4000. So for that I search it here at the bottom. Let's take this one and I just selected it. Once I open, this is like common to just remap. We no longer need to save it again and again, but I just want to show you what's actually present inside the subcircuit. So whatever ICs are there, they are categorized in two ways. One is the digital ICs and one is the analog, or I will definitely say that a TTL logic made IC. It means like it is made from a scratch from the transistor level, like, and the other is like being created using the Verilog code. As yesterday evening session we discussed how to create a model and how to get it added. So yeah, so this is the inside structure of that particular IC, and we can, once we take it here in the canvas, we can directly use it in our application. In case someone want to use it, how they will can do, there is an option called symbol editor. One need to click it here, and then it gives a wide range of library. As I spoke already, we need to work on eSIM underscore library. So the best way to put it is in this folder, eSIM underscore subcircuit, or it is okay if you create your own library also, library folder. It's on the user perspective, whatever convenient is there. Now in eSIM subcircuit, there are multiple library. If I double click on any, I can get a symbol of that. If someone wants to change the symbol, they can do it from here. And if someone wants to add one new symbol in that, then just need to click on eSIM subcircuit, keep it clicked, and we'll click on file and then add a new symbol. Here one thing I wanna just say to everyone, there is a difference in the designator that we are using. eSIM eSIM is structured in a way that whenever you use designator U, it thinks the symbol is made using the Verilog, that is done by ngVery, and then model has been created and uploaded. So whenever we do make anything from a scratch means we are making everything on the canvas, maybe with the example of transistor or whatever components are there in the library. That time we will use the designator capital X over here, and we can name it anything. For now I'm just writing as a test. I will click OK. So now I got the option to edit the symbol. So whatever the example is, I can press M and I can take it out. While doing that, we can take a rectangle, circle, lines. This is for the appearance perspective, how you want that things to be look. And to add pins, this is the first option that I will add, like a pin name IN1, pin number 1. I will click OK. I will add it here, and then I will take out pin number 2. I will keep it here. So in this way, what we can do, we can design our own symbol, and once it is done, I will just save it. So if I want that symbols to be added here, I will press A, and that example name was test. Here you can see it is stored in eSIM subcircuit. I will press OK. Now I have my own symbol for it. So whatever circuit we want to add it here, we need to use the function called new subcircuit schematic from this fourth option. We need to use it and make the circuit, but this time that circuit should not have any sources, it should have the ports. This is called port. What it do? This is port 1 and this is port 2. And how it is related to our earlier circuit, you can see when I was designing this symbol, I myself given this IN1 name and I only give the port name as 1. Here also I give 1, so I need to change it. To change anything in the symbol, the only way to do is you need to click it here for the symbol editor, and then you need to manually locate that file, or you can search it here like a test, double click on it. You can see this is still pin number 1. I will keep it pin number 2 and direction as out. I will save it. Once it's saved, it won't automatically get refreshed. You need to delete that component. You need to add it again, and I will press OK. So now you can see this is the 1 and 2. This is pin number 1, pin number 2, IN1 and out. And as I said, the internal circuitry should have port. How to get port? Port is here only in the library. Yeah. So in that way, I think my screen. Hmm. So this in1 and in2, as I said, the only thing is you need to map the ports accordingly. To add the ports, we need to press A, and in this you need to search PORT port. So this port comes under easy miscellaneous. You need to double click on it and you will get a port. So whenever you start using port, the way to do is click once, you will get a new port, click twice, you will get the next, and multiple time you can add ports. So we have 26 ports for now, and you can use the same ports again in case you want to connect it in the internal. So this is the way. So let me summarize whatever I talked for now, where we seen transient, DC and AC, and we explored symbol creation, we explored the model creation, and we saw how things actually are linked, and I've shown you some examples. So I request everyone to download yesterday's example, try it by yourself once, and in case found any difficulties to do so, you can kindly mail us at contact@esim@fossee.in, keeping me and my team in CC. We'll definitely reach out to you back with the solution. For now, whatever we did was halfway rectifier. We did tested the flat top example. Do anyone completed the natural sampling that I spoke yesterday? Anyone in the audience has performed the anyone performed the natural sampling that like that was like for assignment kind of thing. We will speak on NGS till tomorrow. Yeah, fine. So we are having one beautiful session tomorrow on particularly on EDA tools by Professor Morina Ghosh, who is associate professor in Department of Electronics and Communication at Triple IIT Guwahati, and she will be talking on EDA tools. After that, our team lead Sumantakar sir will be giving a overall demo where everything will be again get covered, each and every feature of eSIM, and just after that we will be having the afternoon session, and that's like overall thing that we did.
Yeah. So any queries till now? Any queries? All the participants, any queries regarding designing or something? No queries as such? Everything is fine? Or do you want to end it soon? So there are some parts of Sky 130 still remaining. So would you like to listen now or afterwards, tomorrow sometime? Where will I be covering everything? Just say yes, no, something. Faculty members, tomorrow, now. I mean, I will just brief what all things are available in eSIM related to Sky 130. Yeah. Just type in the chat box. Just thumbs up is like yes or no. Next session, okay. Anyone else? Okay. Anyone else? Many of you are saying next session. Anyone wants today? Okay. Okay, sure then. Thanks for joining and patiently listening to us throughout the session. So by then, tomorrow we will discuss about NGSDL. I will brief about the converters available in eSIM, and we have Ladek Gravinsky as well after the session of Maureen Ghosh. We have in the afternoon half we have Ladek Gravinsky, who is from the IHP Fab at Germany. So please do join tomorrow at 10:30 a.m. and Ladek's session will be interesting. The session by Professor Morina will also be interesting, and I will also demo you how to work with IHP PDK with eSIM 2.5. So and yeah, and yeah, that's all. Converters in eSIM, and yeah. Let me know if anything, any demand from your side. Just feel free to mail us in case you want something especially to be demo to you. Just mail us. I'm sending the mail ID again. If you need something to be done explicitly, then let us know. Sorry, there is a mistake. What are the send the correct one? Yeah. Okay. So just mail us if you specifically need something to be demoed. Okay then. Thank you. Thanks for joining. Bye.